What if everything you've ever seen, the stars, the galaxies, the atoms in your body, the light from your screen right now, all came from absolutely nothing? Not just from emptiness or a vacuum, but from a state where even existence itself didn't exist? No time, no space, no matter, no energy, no laws, no rules. The most profound question in science, philosophy, and human wonder might be this: how could everything come from nothing? But before we continue, subscribe to the channel and like the video. This isn't merely an exercise in imagination, it's a puzzle at the heart of modern physics and cosmology. We look up at the night sky and see distant galaxies billions of light years away. We measure radiation left over from the Big Bang. We simulate particle collisions and probe deep into the subatomic world, trying to peer back to the very first moments of the universe. But before all of this, before time could tick or space could stretch, was there a moment when nothing existed? And if so, how did this nothingness birth the universe? There's something haunting and almost poetic about the idea that the universe may have come into existence not because of some pre-existing material, but from a pure absence, a void, a silence broken only by the first flicker of being. But that void may not be as empty as we once thought. In fact, the more we study the nature of nothingness, the more we realize it's bursting with potential. Our journey today isn't just about physics, it's about existence itself. We're going to explore some of the deepest ideas humans have ever pondered, guided by quantum theory, cosmology, and philosophical reasoning. We'll travel to the edge of time, dive into quantum vacuums, consider the birth of space, the rise of particles, and the mysteries of the laws of nature themselves. We'll challenge what we think nothing even means and question whether there was ever a true beginning. So buckle in. This isn't just another science explainer. This is a story of how everything, all that you are, all that you know, all that is, might have emerged from the ultimate paradox, that sometimes, from nothing, comes everything. At first glance, nothing seems like a simple concept. It's the absence of everything, right? If you take all matter out of a room, all the air, all the light, every particle, you'd think what remains is nothing. But that's not truly nothing in the eyes of modern physics. That's just a vacuum, a space devoid of matter perhaps, but still very much something. It still has volume. It still exists in time. And crucially, it still obeys laws of physics. The concept of nothing becomes slippery the more deeply we try to define it. Philosophically, nothing is the absolute negation of being: no space, no time, no fields, no laws, not even the potential for something to arise. But in physics, especially in quantum mechanics and cosmology, nothing has taken on a more nuanced meaning, one that seems paradoxical at first, but becomes illuminating as we probe further. What scientists often mean when they say, nothing, isn't an absolute void, but a quantum vacuum. And this so-called vacuum, it turns out, is anything but empty. It's a seething froth of activity at unimaginably small scales. Particles flicker in and out of existence, energy levels fluctuate, and the fundamental fields that underpin reality never sit perfectly still. Even if you stripped away all known particles and cooled everything to absolute zero, the coldest possible temperature, the vacuum wouldn't go silent. It would still shimmer with uncertainty and potential. This is why nothing, in modern physics, is not the absence of existence but a kind of potential state, a field with zero particles but non-zero possibility. The laws of quantum field theory suggest that even when all matter and radiation are removed, what's left is still governed by principles. There are still quantum fields permeating space. There's still a framework within which fluctuations can occur. Imagine a perfectly flat, quiet ocean. You might say there are no waves, nothing is happening, but under the surface, microscopic motions are still taking place. Water molecules are jostling, tiny eddies are swirling, and deep forces are at play. This is similar to how physicists view the quantum vacuum, not a lifeless void, but a dynamic medium rich with subtle activity. And here's where things get even more interesting. If we go beyond even the quantum vacuum, to what existed before space itself, we hit a conceptual wall. Can we even speak of a before, if time didn't exist yet? Can we imagine space being created if there was no place to create it in? When scientists hypothesize about the true nothingness before the Big Bang, they're not picturing an empty darkness. They're confronting a kind of non-being that defies imagination. Not an empty universe, but no universe at all. This is why the word, nothing, must be handled carefully in physics. Because most of the time, when physicists say that the universe emerged from nothing, they mean from a quantum vacuum, or a zero-point field, or from a symmetry state where total energy is conserved in such a way that existence doesn't violate any laws. It's not creation ex nihilo in the purest philosophical sense. It's more like a reconfiguration of what didn't yet express itself as something, a rearrangement of potential, sparked by fluctuations in a field that didn't yet have form. There's also an important point to consider: the rules of quantum physics, the logic of fluctuation, uncertainty, energy conservation. These seem to pre-exist the universe. Or at the very least, they were baked into the fabric of existence the moment the universe began. But if the laws themselves are required to allow something to arise from nothing, then we must ask, where did the laws come from? Are they eternal, like mathematical truths? Or are they themselves emergent from some deeper, unknowable source? It's tempting to try and draw a clear line, to say, before the universe, there was nothing. Then something happened. And now we're here. But that sequence only makes sense if time existed before the universe. And most cosmologists argue that time itself began with the Big Bang. In that case, asking what came before is like asking what's north of the North Pole. The question collapses because the coordinates themselves don't apply. So when we ask, how could everything come from nothing? We have to redefine what nothing actually means. And in the context of our universe, nothing may not be an absence, but a zero state of something deeper, a primordial canvas governed by uncertainty, fluctuation, and latent structure. A kind of pregnant silence, filled with hidden potential, ready to erupt into existence not through magic, but through the rules of quantum reality. This redefinition of nothing sets the stage for what comes next, because if the vacuum isn't empty, and if nothingness can fluctuate, then maybe, just maybe, the seeds of the cosmos are already planted in the concept of nothing itself. To the naked eye, outer space seems like a vast, silent void. A cold, black emptiness stretching between stars and galaxies, seemingly devoid of anything at all. But as science has pulled back the layers of that darkness, a shocking revelation has emerged: space, even when stripped of all matter and radiation, is far from empty. The quantum vacuum, what we used to consider nothing, is actually a teeming ocean of invisible activity. It's a restless, energetic medium where particles flash into and out of existence, where energy pulses unpredictably, and where the laws of quantum mechanics ensure that absolute stillness is impossible. This isn't just theoretical poetry, it's experimentally verified physics. In the 20th century, quantum field theory revolutionized our understanding of the vacuum. Rather than treating empty space as a blank canvas, it revealed that every point in space is actually filled with quantum fields, invisible, omnipresent energy fields that fluctuate constantly. These fields aren't passive. They're the fundamental reality. Everything in the universe, electrons, photons, quarks, even the Higgs boson, is just an excitation or ripple in one of these underlying fields. When we say vacuum, we usually mean a region of space with no particles, no light, no heat. But in quantum field theory, even this purest vacuum still has structure. Even in its lowest energy state, each quantum field is never perfectly calm. There are always tiny, random fluctuations, like ripples on a seemingly still pond. These fluctuations aren't caused by anything external. They are an inherent feature of the quantum nature of reality. They happen because of a deep principle in quantum mechanics: uncertainty. In this view, empty space is more like a simmering broth than a frozen void. One of the most mind-blowing confirmations of this came from the Casimir effect. In the 1940s, Dutch physicist Hendrik Casimir predicted that if you place two uncharged, perfectly conducting plates extremely close together in a vacuum, they would mysteriously be pushed toward each other. This wasn't due to any conventional force, but rather to the energy of the vacuum itself. The quantum fields between the plates were constrained in a way that allowed fewer modes of fluctuation than outside the plates. The imbalance in vacuum energy created a net force, measurable, real, and entirely due to the emptiness of space. This vacuum energy isn't just a laboratory curiosity, it has implications on a cosmic scale. In cosmology, vacuum energy is thought to drive the accelerated expansion of the universe. The mysterious force we call dark energy, which is causing galaxies to fly apart at an ever-increasing rate, may be nothing more than the energy of the vacuum itself, an unseen, undying pressure that fills the universe like an invisible gas. And if you zoom in small enough, unimaginably small, to the Planck scale, space becomes a churning foam of fluctuations. Space-time itself begins to ripple and twist due to the frenetic energy of quantum processes. It's a realm where classical ideas of space and time break down, and where uncertainty reigns. Some theories even suggest that space-time itself may be emergent from these fluctuations, not something that exists independently, but something that rises up out of this quantum storm. It's almost ironic, the closer we get to nothing, the more we find something. The vacuum is not a passive backdrop. It's active, creative, and absolutely essential to the universe's structure. Particle physics, cosmology, and quantum mechanics all rest on this idea that even when you take everything away, the vacuum remains. And the vacuum is alive. The implications are profound. If fluctuations in the quantum vacuum are always happening, then perhaps they could be the seeds of matter, energy, and even entire universes. In this sense, nothingness becomes the ultimate source of creativity. A fluctuating vacuum doesn't just allow for something to emerge, it practically demands it. So when we ask how matter could come from nothing, we're not imagining particles suddenly appearing in a true void. We're talking about how, under the strange and beautiful rules of quantum physics, the vacuum itself provides the canvas, the paint, and the brush. It is the fertile soil from which reality can bloom, without any need for a prior universe, or even time as we understand it. From this perspective, nothing is more like a hidden engine, one that pulses with possibility. The quantum vacuum may look like a featureless expanse, but deep down, it's bursting with energy. It may be silent to our ears and invisible to our eyes, but it's anything but empty. It's the birthplace of reality, humming with the potential to create stars, galaxies, and even life itself, from the deepest silence ever imagined. At the heart of quantum physics lies an astonishing principle. Even the most seemingly stable, unchanging conditions are never truly still. The universe, down to its smallest scales, is forever in motion, unpredictable, chaotic, and alive with energy. This is the realm of quantum fluctuations, tiny, momentary changes in the energy of a point in space, born out of the restless nature of quantum fields. They are the subtle yet foundational tremors of the universe, and they may hold the key to understanding how matter itself could spring from what appears to be nothing. To grasp quantum fluctuations, we first need to understand that in quantum field theory, the framework that unites quantum mechanics with special relativity, the universe isn't made of solid particles floating in space. Instead, it's composed of fields. Every type of particle is associated with a corresponding field that stretches across the cosmos. An electron is just a ripple in the electron field. A photon is a ripple in the electromagnetic field. These fields exist everywhere, even in what we perceive as empty space. Now, here's the strange part. Even when these fields are in their lowest energy state, what we'd expect to be a calm, undisturbed equilibrium, they're not flat or still. Because of quantum uncertainty, they constantly fluctuate. These fluctuations are spontaneous and unavoidable. They occur even when no energy is being added, and no external forces are acting. They are, in a sense, the universe's default behavior. Quantum fluctuations can be thought of as the fields, borrowing tiny amounts of energy for incredibly brief periods of time. This idea is rooted in the Heisenberg uncertainty principle, which tells us that certain pairs of physical quantities, like energy and time, can't both be precisely known at once. The more precisely you know the energy of a system, the less precisely you know how long that energy state will last, and vice versa. This uncertainty creates a loophole that nature exploits constantly. For short enough durations, the uncertainty in energy allows the vacuum to spontaneously generate small bursts of energy. These bursts can give rise to what are known as virtual particles, pairs of particles and antiparticles that momentarily flicker into existence, only to annihilate each other and vanish again almost instantly. They're called virtual because they don't exist long enough to be directly observed, and they don't violate conservation laws because the borrowed energy is paid back so quickly that, on average, no net energy is lost or gained. This might sound like science fiction, but it has real, measurable effects. The forces between particles, for example, are influenced by these fluctuations. In quantum electrodynamics, QED, the most accurate theory in physics, interactions between electrons and photons depend on the sea of virtual particles swarming around them. Even the behavior of fundamental constants, like the strength of electromagnetic interaction, is subtly affected by the activity of quantum fluctuations. One famous consequence of this is vacuum polarization. Imagine placing an electron in space. Around it, virtual particles constantly pop in and out of existence, and their presence slightly alters the electric field of the electron. The cloud of virtual particles makes the electron's field seem different from what we would expect if the vacuum were truly empty. This shows that nothing, even the purest vacuum, behaves like something, influencing forces, energy, and motion in ways that would be impossible in a truly inert void. The more we probe this quantum dance, the more we see that quantum fluctuations aren't just background noise, they are creative. They introduce randomness and uncertainty into the universe, yes, but they also allow for emergence, change, and evolution. They lay the groundwork for the spontaneous formation of structure. Without them, the universe would be sterile and lifeless. But perhaps most intriguingly of all, quantum fluctuations are the leading contenders for explaining how the early universe got its first irregularities. The tiny, uneven patches of energy that would later grow into galaxies, stars, and eventually planets and life. If, in the very first moments after the Big Bang, these fluctuations occurred within a rapidly expanding space, they could have been stretched and amplified across the cosmos, becoming the seeds of cosmic structure. From the most microscopic uncertainty could emerge the grandest of designs. This raises an extraordinary possibility that everything we see, the galaxies, the stars, the Earth, and all living things, might have originated from a random flicker in a field that couldn't sit still. From nothingness emerged a pattern. From vacuum emerged substance. From quantum fluctuations, perhaps, emerged everything. To understand how particles can seemingly appear and disappear from nowhere, we must journey deeper into the strange terrain of quantum mechanics, and at its heart lies the Heisenberg uncertainty principle. This isn't just a scientific oddity, it's a fundamental truth woven into the very structure of our universe. The uncertainty principle doesn't simply reflect a limit in human measurement, it reveals that reality itself is inherently indeterminate on the smallest scales. And this indeterminacy allows the impossible to become possible, for particles to pop into existence, defy traditional logic, and vanish without a trace, all within the blink of the quantum eye. Formulated by Werner Heisenberg in 1927, the uncertainty principle states that there are pairs of physical properties which cannot be precisely known at the same time. The most famous of these is position and momentum. The more precisely you know where something is, the less precisely you can know how fast it's moving and in what direction, and vice versa. But this principle also applies to other quantities, especially energy and time. The more precisely you measure the energy in a system, the less certain you can be about how long that energy lasts. Conversely, if an event occurs over a very short time interval, then the uncertainty in its energy can be large. Now, this isn't just a measurement problem, it's not about faulty instruments. It's about the fabric of quantum reality. The universe doesn't allow sharp edges in the quantum realm. There's a kind of inherent fuzziness, a built-in wiggle room that can't be eliminated. On the tiniest scales, particles don't have fixed positions or fixed energies. Instead, they exist in a haze of probability, described not by certainties but by wave functions that express a range of possible values. This intrinsic uncertainty gives rise to one of the most bizarre and essential consequences in physics: the temporary violation of energy conservation on extremely short timescales. Because the universe allows energy to be borrowed, as long as it is paid back quickly enough, particles can momentarily spring into existence out of the vacuum. These are the so-called virtual particles, not permanently real, but fleeting ghosts of matter and energy. They arise from the foam of uncertainty, perform their quantum dance, and then vanish into the silence from which they came. It may sound like a loophole, and in a way it is. But it's a loophole nature uses constantly. Without this principle, atoms couldn't exist. Electrons wouldn't be confined to orbitals. The stability of matter itself, the fact that we don't collapse into nothingness, relies on quantum uncertainty. The behaviors of the smallest particles are governed not by certainty, but by chance, and yet this randomness gives rise to order. In the vacuum of space, the uncertainty principle ensures that there is always a seething froth of activity. No region of space can be truly still. Even the emptiest point in the universe is alive with quantum jitters. These jitters are not optional. They are demanded by the laws of nature. Particles may appear seemingly from nowhere, briefly interacting with the universe, and then disappear again, all within a time window permitted by the uncertainty between energy and time. To make this more concrete, consider the idea that a virtual particle and its antiparticle could suddenly exist for just long enough that the uncertainty in their borrowed energy doesn't violate the laws of physics. The more energy they borrow, the shorter the time they can exist. The less energy they borrow, the longer they can linger. This cosmic bookkeeping ensures that, over the long run, energy is conserved, but in the short term, the vacuum becomes a playground of spontaneity. This quantum instability, this inability of reality to hold perfectly still, isn't a flaw. It's a feature. It's what gives the vacuum its texture. It's what powers fundamental processes like Hawking radiation, where black holes slowly evaporate by radiating away particles born at their event horizons, particles conjured into existence by quantum uncertainty. It's what allows forces to be mediated by virtual particles, like photons flickering between charged particles, or gluons binding quarks together. And this same uncertainty might have been what allowed our entire universe to begin. If space and time didn't exist before the Big Bang, and if there was no prior framework for particles or energy, then how could anything begin? The answer may lie in uncertainty itself. In a reality where nothing is fixed, where the vacuum is never completely at rest, where energy can briefly emerge from a zero-point field, the spontaneous birth of the universe becomes less absurd. It becomes, in some sense, inevitable. If fluctuations can exist without cause, if the universe plays by quantum rules even when there's nothing to play with, then the Heisenberg uncertainty principle is not merely a quirk of the small, it may be the reason that something, rather than nothing, exists at all. In the surreal world of quantum physics, perhaps nothing is more astonishing than the notion that particles, actual, physical entities, can flicker into existence out of the vacuum, linger for a fleeting moment, and then vanish without a trace. This idea isn't speculative science fiction, it's a consequence of the Heisenberg uncertainty principle and the peculiar behavior of quantum fields. These ephemeral entities are known as virtual particles, and they are a constant, invisible presence in what we once believed to be the empty void of space. Let's begin by returning to the quantum vacuum, not a simple absence of matter, but a vibrant quantum stage, humming with activity. At every point in this vacuum, quantum fields fluctuate unpredictably. These fluctuations sometimes grow large enough to momentarily manifest as pairs of particles and their corresponding antiparticles. A virtual electron may appear alongside a virtual positron, its antimatter twin, before the two annihilate each other, returning their energy to the vacuum. These particles are called virtual because they do not obey the same rules as regular particles. They can break the traditional laws of energy conservation, but only very briefly and only within the boundaries set by the uncertainty principle. They are not directly observable in isolation because their lives are too short, and their existence is tied intimately to the mathematics of quantum interactions rather than to classical notions of objects with persistent presence. Yet their effects are real, measurable, and woven into the structure of the universe. One of the most compelling demonstrations of virtual particles at work is in quantum electrodynamics, QED, the highly accurate theory that describes how light and matter interact. In QED, the forces between charged particles, like electrons, aren't mediated by literal, flying particles in the classical sense. Instead, these forces are described in terms of exchanged particles, specifically virtual photons. When two electrons repel each other, it's because they are exchanging virtual photons, constantly trading these ghostly messengers back and forth. These photons never exist long enough to be seen, but their presence is required by the math, and by the reality we can test in high-precision experiments. Even more fascinating is the influence of virtual particles on observable phenomena. Take, for instance, the Lamb shift, a subtle change in the energy levels of hydrogen atoms that couldn't be explained by classical physics. It was only through accounting for the effects of virtual particles, the influence of fluctuating quantum fields on the electron in the atom, that physicists could explain the discrepancy. Similarly, the anomalous magnetic moment of the electron, measured to an extraordinary level of precision, also reveals the fingerprints of virtual particles. If they didn't exist, the numbers wouldn't add up. Another striking phenomenon involving virtual particles is the Casimir effect, as previously mentioned. When two metal plates are placed very close to each other in a vacuum, they experience a tiny but measurable force pulling them together. This is not due to any classical electromagnetic attraction, but rather to the suppression of certain quantum vacuum fluctuations between the plates. The allowed modes of virtual particle pairs are restricted by the boundaries the plates impose, leading to a net imbalance in pressure, a pressure created by nothing. It's as if the vacuum itself is pushing the plates together because there are more virtual particles acting on the outside than between the plates. But the consequences of virtual particles are not confined to laboratory curiosities. They extend all the way to the edges of black holes and the early moments of the universe's birth. Stephen Hawking's famous prediction of Hawking radiation is rooted in the behavior of virtual particles. At the event horizon of a black hole, the boundary beyond which nothing can return, quantum fluctuations can cause a pair of virtual particles to appear. Normally, these would annihilate each other almost instantly. But if one falls into the black hole while the other escapes into space, the escapee becomes a real particle, carrying energy away. To conserve energy, the black hole loses mass, effectively evaporating over time. This means that virtual particles, born from the vacuum, can have permanent, universe-altering consequences. Even more profound is the role virtual particles may have played in the inflationary period of the early universe. During inflation, a period of incredibly rapid expansion just after the Big Bang, the vacuum itself was expanding. In this expanding space, virtual particles that would normally cancel each other out could be stretched apart faster than they could recombine. When this happened, they could become real particles, locked into existence by the sheer scale and speed of cosmic expansion. These particles could then go on to form the seeds of all the matter in the cosmos. What was once a fleeting fluctuation became the ancestor of galaxies, stars, and human beings. This idea, that virtual particles could transition from nothing more than temporary quantum blips to permanent building blocks of the universe, fundamentally challenges our understanding of origin. It forces us to recognize that the fabric of reality is deeply probabilistic, that particles need not arise from other particles, and that the vacuum isn't just a passive backdrop but a generator of potential. In the quantum world, empty space is an illusion. It's better imagined as a cauldron boiling with activity, where virtual particles are being created and annihilated in a ceaseless cycle. This activity is subtle and normally hidden, but it underpins much of what we observe. Forces, masses, decay rates, and stability, all are influenced by these unseen players. Moreover, the number of virtual particles is not fixed. At any moment, countless pairs can be created and destroyed. They are not bound by conventional causality in the way real particles are. In fact, within the realm of Feynman diagrams, visual representations of quantum interactions, virtual particles are represented as internal lines, connecting interactions but never appearing at the input or output of a process. They exist within the mathematical scaffolding of quantum field calculations, essential, but always hidden. One might ask, if they can't be directly observed, how can we be so confident they exist? The answer lies in prediction and measurement. The corrections to particle properties calculated using virtual particles match what we observe in particle accelerators and atomic experiments to a degree that defies coincidence. QED, with its reliance on virtual particles, has been tested to parts per trillion, the most precise agreement between theory and experiment in the history of science. There is something beautiful, and deeply unsettling, about this. The most accurate physical theory ever created rests on entities that flicker in and out of reality, that live in the shadows of existence, that are permitted by uncertainty and powered by the vacuum. It suggests a universe that is never fully at rest, a universe where what we see and touch is only a tiny sliver of a deeper, more vibrant quantum truth. So next time you consider the vast emptiness of space, remember this: it is anything but empty. It is alive with fluctuations, flickering with virtual particles, vibrating with the unseen rhythm of existence. And from this strange, restless sea, from these ghostly whispers of energy, might have emerged everything. If the vacuum of space is constantly alive with virtual particles, fleeting phantoms born from quantum fluctuations, then a profound question naturally follows: can these ephemeral events actually create real, lasting matter? Can particles that emerge for only a split second somehow become the seeds of entire galaxies, stars, and life itself? This question goes to the heart of modern cosmology, and the answer, while not simple, is one of the most astonishing implications of quantum physics. Virtual particles, by definition, exist for extremely short periods of time and cannot be directly observed. They arise spontaneously from the quantum vacuum and disappear just as quickly, never existing long enough to leave a permanent trace in our macroscopic world. Yet, under certain conditions, what begins as a temporary fluctuation can become something enduring. The key lies in the interplay between these fluctuations and the environment in which they occur, particularly when that environment is not static, but expanding. To understand how fluctuations can become real matter, imagine the very early universe, just moments after the Big Bang, or, more accurately, just after the universe began to expand. During this time, the universe underwent a phase called inflation, which we'll explore more deeply later. In brief, inflation was an extremely rapid expansion of space itself, faster than the speed of light, that occurred in a tiny fraction of a second. This expansion wasn't like a balloon inflating in a room. Rather, it was space itself stretching, carrying everything with it. Now picture quantum fluctuations happening in that wildly inflating space. Under normal circumstances, virtual particle pairs appear and then annihilate quickly, vanishing before they can influence anything. But during inflation, the rules change. Space is stretching so fast that these particle pairs can be separated before they have the chance to annihilate each other. Once torn apart by the expansion of space, they become effectively frozen in place, unable to reunite, and cancel out their existence. In this way, what would have been a brief, unnoticeable event in a stable vacuum becomes a permanent imprint in the fabric of the universe. This process, the conversion of quantum fluctuations into real, classical disturbances, is believed to be the origin of the primordial density fluctuations in the early universe. These tiny differences in energy density eventually led to the formation of galaxies and all large-scale cosmic structures. The process doesn't create fully formed atoms or matter right away. Instead, it lays down the blueprint, regions that are ever so slightly denser than others, which gravity will later act upon, causing matter to clump, cool, ignite, and form stars. But can the fluctuations do more than just shape energy into structure? Could they actually create particles, the fundamental constituents of matter, from nothing but the vacuum itself? In the context of the early universe, the answer appears to be yes. During and immediately after inflation, the universe underwent a process known as reheating. As the inflationary field, the field responsible for driving the rapid expansion, decayed, its immense energy was released into the universe, creating a hot, dense soup of particles. This wasn't like lighting a fire. It was more like a field collapsing and unleashing its stored energy into the universe. That energy, governed by Einstein's equation, was capable of forming real, massive particles. In this way, the quantum fluctuations, stretched by inflation and energized by reheating, could transition from mathematical ripples into actual matter. The vacuum itself, though not truly nothing, gave rise to everything we know. Fields created particles. Particles gained energy and mass. Interactions began. The universe, once a frothing field of potential, became a place of substance and structure. This transformation also introduces the idea that the universe didn't need an external input to become populated with matter. There was no outside source feeding particles into the universe. Instead, the vacuum, energized and destabilized by inflation, was capable of generating real particles internally. Matter arose not from pre-existing matter, but from energy embedded in the structure of space itself. Today, we even observe this process, in miniature, in laboratory experiments. Under extreme conditions, like near black holes, in high-energy particle accelerators, or in regions of intense electromagnetic fields, virtual particles can become real. One theoretical prediction, the Schwinger effect, suggests that in a strong enough electric field, virtual particle pairs can be torn apart and become real, much like during inflation. While we haven't yet achieved the required field strength to observe the Schwinger effect directly, it serves as a powerful theoretical validation of this phenomenon. Another extraordinary concept is Unruh radiation, a predicted effect where an accelerating observer in a vacuum would detect a thermal bath of particles where an inertial observer would see none. This too implies that what is real, and what is virtual, can depend on perspective and environment. Under the right conditions, quantum fluctuations are not just allowed to become matter, they're required to. So, can fluctuations create real matter? Theoretical physics, observational cosmology, and quantum field theory all converge on a remarkable conclusion: yes. Not only can they, but they did. The matter in your body, the screen you're looking at, the stars in the night sky, all may have originated from fluctuations in a quantum field, amplified by cosmic expansion, energized by the decay of inflation, and crystallized into particles by the unrelenting logic of quantum mechanics and relativity. This view doesn't just challenge the classical idea of cause and effect, it redefines it. Creation didn't need a sculptor. It didn't need raw materials. It needed instability, uncertainty, and laws that allowed the improbable to become inevitable. In this strange quantum reality, what begins as a jitter in the void can become the fabric of galaxies. So when we asked if real matter can emerge from nothing, the answer is yes, as long as nothing contains the quantum fields and laws that make fluctuation possible. In other words, matter wasn't added to the universe. Matter was always a possibility embedded within the rules of physics themselves. The vacuum was always pregnant with reality, and under the right conditions, it gave birth to everything. To understand how quantum fluctuations could be stretched into real matter, we must dive into one of the most groundbreaking ideas in modern cosmology: cosmic inflation. This theory takes the eerie and seemingly abstract dance of quantum fields and magnifies it, literally, to cosmic proportions. Inflation is not just a clever addition to Big Bang theory. It reshapes how we think about the very beginning of the universe and how something could emerge from what was, at first glance, nothing. Inflation describes a moment in the early universe when space itself underwent an unimaginably rapid and exponential expansion. This wasn't just a normal kind of growth, not like a balloon slowly inflating. This was a violent eruption of space-time, expanding by a factor of at least in less than seconds. It took the entire observable universe, currently spanning over 90 billion light-years, and blew it up from a subatomic scale. The idea of inflation was introduced in the early 1980s, most notably by physicist Alan Guth, to address several glaring issues with the classical Big Bang model, particularly the horizon problem, the flatness problem, and the monopole problem. But beyond solving these puzzles, inflation had an extraordinary byproduct: it transformed quantum fluctuations into the seeds of all structure in the universe. Here's how it works. During inflation, the universe was dominated by a mysterious form of energy often referred to as the inflaton field. This scalar field, filling all of space, possessed a high-energy state that drove the rapid expansion. But like all fields in quantum mechanics, the inflation field wasn't perfectly smooth. It fluctuated randomly due to quantum uncertainty. These fluctuations, while tiny on microscopic scales, were baked into the universe itself. They were not floating within space. They were part of the expanding fabric of space-time. Now here's the incredible part. Because space was expanding so fast during inflation, those microscopic fluctuations were stretched to macroscopic scales. In essence, tiny ripples in the quantum fields were pulled apart so quickly that they were frozen into place. Once they were stretched beyond the cosmological horizon, the maximum distance over which information could travel, they could no longer smooth out. They became imprinted as permanent features of the universe's energy density. These fluctuations were no longer mere momentary quantum jitters. Inflation effectively turned them into classical perturbations, stable, large-scale variations in energy density across space. Over time, gravity acted on these denser regions more strongly, causing matter to accumulate there, eventually leading to the formation of stars, galaxies, and clusters. In other words, the structure of the entire universe, all the cosmic filaments, galactic walls, and voids, began as quantum foam, magnified by inflation. It's important to note that this doesn't violate any known laws of physics. In fact, it follows naturally from quantum field theory in an expanding space-time. Inflation takes the same quantum rules we use to describe particles and applies them to the fabric of space itself. And unlike virtual particles, which are confined by the uncertainty principle to exist only fleetingly, these inflation-stretched fluctuations become permanently etched into reality by the sheer speed of expansion. The mathematical framework behind this idea is not only elegant, it's also predictive. One of the key predictions of inflation is the spectrum of primordial density fluctuations, a specific pattern of tiny temperature differences in the early universe. These predictions are confirmed in exquisite detail by observations of the cosmic microwave background (CMB), particularly through missions like WMAP and Planck. The CMB reveals slight variations in temperature and density across the sky, corresponding precisely to the statistical properties expected from inflationary quantum fluctuations. Moreover, inflation doesn't just explain how fluctuations grew into structure, it provides a mechanism for how energy itself could become matter. After the period of inflation ended, the inflaton field didn't just vanish, it decayed. Its energy was converted into a hot, dense plasma of particles through a process known as reheating. During reheating, the stored vacuum energy of inflation was unleashed into the universe, heating it to incredible temperatures and filling it with a sea of fundamental particles. This moment marks the beginning of the more traditional hot Big Bang phase, the era in which particles interact, combine, and evolve into atoms and eventually complex matter. But crucially, inflation set the stage. It provided not just the geometry and structure of the universe, but also the raw energy required to birth matter from fields. In essence, inflation is the bridge between the strange, uncertain world of quantum fields and the tangible reality of particles and forces. And yet, this mechanism is deeply counterintuitive. It tells us that the initial conditions of the universe were not chaotic or irregular. In fact, inflation predicts a universe that is incredibly uniform and flat on large scales, exactly what we observe. But within that smoothness lies a delicate tapestry of tiny fluctuations, each a whisper from the quantum world, each magnified into a galactic nursery. Think of it like this: imagine a flat, calm pond with barely noticeable ripples on its surface. Now imagine rapidly freezing that pond mid-ripple and then expanding it 1 billion times over. Those tiny waves are now enormous patterns, carved permanently into the ice. In much the same way, inflation froze and expanded quantum fluctuations, embedding them into the expanding universe. Perhaps the most awe-inspiring aspect of inflation is that it doesn't just explain the what or the how, it redefines the possible. It shows us that the cosmos doesn't need a pre-existing architecture, a set of prearranged particles, or even a clear cause. Given a field, quantum mechanics, and space capable of expansion, the rest follows naturally. The vacuum, energized by inflation, becomes a cosmic generator, a mechanism that doesn't just allow something to emerge from nothing, it demands it. And inflation might not be a one-time event. Some models propose eternal inflation, in which inflation never completely ends but spawns countless bubble universes, each with its own physical laws and structures. In this view, our universe is just one out of potentially infinite others, each birthed from the quantum fluctuations of an inflating field, each a ripple in a vast multiversal ocean. So when we ask how fluctuations can become matter, inflation offers an elegant, deeply compelling answer. It shows that randomness, when stretched by the geometry of spacetime, becomes pattern. That noise, when amplified by expansion, becomes structure. And that the quantum haze of nothingness, when driven by the right conditions, becomes everything. Before the beginning, there was no space, no time, no matter, no light, no darkness. There was not even a before, because time itself had not yet emerged. This is the concept we confront when we speak of the Big Bang, not as an explosion in space, but as the origin of space and time themselves. When we say that the universe began around 13.8 billion years ago, what we mean is not that something happened within the universe, but that the very framework that allows for events, the stage of space-time, was born in that instant. This idea is almost impossible to grasp intuitively. Our everyday experience is built upon space and time. Everything we do is located somewhere and happens sometime. We wake up in a room, eat breakfast at a certain hour, drive to a location. We can't imagine an existence without coordinates, without clocks. And yet, when we rewind the story of the cosmos back to its earliest moments, we are forced to abandon those comforts. We are forced to imagine a reality where the rules themselves are not yet written. Let's look back as far as physics allows us. Right now, we can confidently trace the universe's history back to a fraction of a second after the Big Bang, about seconds. At that point, cosmic inflation begins, and soon after, the universe fills with a dense, hot plasma of particles and radiation. As time ticks forward, these particles cool, form atoms, condense into stars and galaxies. All of this is well modeled, backed by observational data, and forms the core of what we call the standard model of cosmology. But as we rewind closer and closer to the moment of creation, the models begin to falter. At around seconds, the Planck time, our current understanding breaks down. This is the scale at which both quantum mechanics and general relativity become necessary, but where we currently lack a unified theory that can reconcile them. At this scale, gravity is as strong as the other fundamental forces, and the concepts of distance and time become so warped that they may lose all meaning. What existed before this moment? From the standpoint of general relativity, nothing. Literally nothing. Not empty space, but no space. Not an empty moment, but no moment. Time itself begins at the Big Bang. This isn't just a philosophical position, it's a mathematical conclusion. If you imagine the equations of general relativity describing the curvature of space-time, they cease to be valid before the Big Bang because the terms that define space and time themselves vanish. It's crucial here to separate popular misconceptions from what physics actually says. The Big Bang was not an explosion in space. It was an expansion of space. It didn't erupt into a pre-existing emptiness. There was no external void waiting to be filled. Instead, the very metrics that define distances and intervals, the rulers and clocks of the cosmos, were born in that moment. The universe was not expanding into anything, space itself was stretching, and continues to stretch. This leads to a subtle but profound idea. The origin of the universe is not an event in time, it is the origin of time itself. And that means we can no longer rely on our everyday logic to probe, before the beginning. There was no before. Not because it's hidden, or inaccessible, but because it didn't exist. Asking what happened before the Big Bang is like asking what's north of the North Pole. It's not just unknown, it's undefined. So what did exist at time zero? The honest answer is that we don't fully know. Our current theories describe what happens after the Planck time, but the true beginning likely requires a quantum theory of gravity, something physicists are still working to develop. One possibility is that space and time emerged from a quantum foam, a wildly chaotic state where classical notions of geometry don't apply. In this view, space and time are emergent properties, like temperature, is an emergent property of the motion of atoms. They're not fundamental ingredients, but behaviors that arise under certain conditions. Some theories go even further. The Hartle-Hawking no-boundary proposal, for example, suggests that the universe had no sharp beginning, that time becomes more like a spatial dimension at the earliest moments, gradually transitioning into what we experience as temporal flow. According to this model, the universe didn't begin with a bang, but with a gentle rounding off, like the south pole of a sphere, smooth, finite, and without boundary. Other proposals posit that our universe emerged from a quantum tunneling event, in which a tiny bubble of space-time spontaneously formed from the quantum vacuum. This bubble then inflated, rapidly expanding into the vast cosmos we observe today. In this model, space and time are not eternal, but they also didn't require a pre-existing realm to emerge from. The laws of quantum mechanics themselves may have made the universe inevitable. What's especially strange is that all of this, the beginning of time, the stretching of space, the rise of structure and matter, may be governed by equations that existed before the universe did. This raises a deep philosophical question: how can physical laws exist without space or time? Are they built into the fabric of reality in some Platonic realm? Or are they themselves emergent, arising only when the universe does? These are questions at the cutting edge of physics and metaphysics alike. But whatever the exact nature of the beginning, one thing is clear: the birth of space and time was not a passive event. It was dynamic, energetic, and creative. The singularity, if such a thing existed, was not a place where things were, but a moment when things began. It was the boundary of the knowable, and from that boundary, reality as we understand it unfurled. From nothingness, not just particles, but the arena in which particles can exist, was born. Space to stretch. Time to flow. Forces to interact. Dimensions to move within. Without space and time, the very language of physics falls silent. With them, the story of the universe begins its first line. And so we must come to terms with a startling conclusion: everything we know, distance, duration, causality, even existence itself, is rooted in that primordial moment. The Big Bang was not just the origin of matter. It was the origin of context. The blank page before the first word. The screen before the first pixel. The emptiness that somehow allowed for fullness. For decades, the standard model of cosmology portrayed the beginning of the universe as a singularity, a point of infinite density, infinite temperature, and zero volume where the known laws of physics cease to function. It is a deeply unsettling idea, not because it implies something physical, but because it implies a breakdown of all physical understanding. A singularity is not so much a place or a thing as it is a signal that the mathematical framework we're using has reached its limits. It's the universe's way of telling us, your current equations do not apply here. In classical general relativity, the singularity emerges naturally when we trace the evolution of spacetime backward in time. Einstein's field equations describe how matter and energy warp the geometry of spacetime, and if you reverse the expansion of the universe mathematically, you arrive at a state where the curvature becomes infinite. This is the classical Big Bang singularity, a mathematical artifact where time, space, matter, and energy are compressed into an undefined point. But physicists are increasingly skeptical of the idea that this singularity is real. Why? Because singularities are signs of incompleteness in a theory. They're the equivalent of getting divide by zero errors in a computer program. And when a theory breaks down at a certain scale, it's usually a clue that we need a new framework that can handle the extreme conditions that the old one could not. In this case, what breaks down is general relativity, and what's missing is the quantum side of gravity. Enter quantum gravity, the elusive, still theoretical framework that seeks to merge general relativity, which governs the cosmos, with quantum mechanics, which governs the microscopic. While we don't yet have a complete and experimentally verified theory of quantum gravity, several leading approaches offer tantalizing clues about what might replace the singularity, a more graceful, physical, and fundamentally quantum beginning of the universe. One of the most well-known candidates is loop quantum gravity, LQG. In LQG, space itself is quantized. Rather than being continuous and smooth, space is made up of tiny, discrete loops, like the fabric of a finely woven mesh. According to this model, the universe did not begin from a singularity but from a quantum bounce. That is, as we trace the universe backward toward its origin, the density and curvature reach a maximum finite value, and then, instead of collapsing to a point, the universe rebounds. In this view, the Big Bang is not a beginning, but a transition, possibly from a previous contracting universe. This is more than just a mathematical trick. Loop quantum cosmology suggests that spacetime has a smallest possible unit, a smallest volume, smallest area, smallest duration, beyond which the very notion of smaller loses meaning. When you apply this to the early universe, the singularity is replaced by a quantum regime where gravity is repulsive at high energies, pushing space-time apart and triggering expansion. In other words, the universe may have emerged from a quantum gravitational state that preceded classical space-time. Another approach comes from string theory, which proposes that the fundamental building blocks of the universe are not point particles but tiny vibrating strings. String theory includes a natural minimum length scale, on the order of the Planck length, meters, below which spacetime cannot be probed. This could mean that instead of a singularity, the early universe was in a highly compacted, but non-zero, state where classical geometry is replaced by a quantum fuzz. Some string theory models suggest the universe began in a state of higher dimensions, which then compactified into the four we experience, 3 spatial, 1 temporal, avoiding a singularity entirely. In both loop quantum gravity and string theory, what we get is a quantum genesis, a beginning not of infinite density, but of high energy, non-classical, non-singular states. These states may be governed by a different set of rules, or even different notions of causality, time, and geometry. The smooth, predictable evolution of spacetime we observe today would then be a low-energy approximation of much stranger, earlier rules. Another tantalizing idea is the no-boundary proposal, developed by James Hartle and Stephen Hawking. This model uses the principles of quantum mechanics to suggest that time itself might have behaved like a spatial dimension at the very earliest moments. Instead of a singular beginning, the universe could have undergone a kind of quantum tunneling from nothing, where nothing is defined as a timeless, spaceless quantum state. In this framework, the universe has no initial singularity and no edge in time. It simply transitions smoothly from a timeless quantum realm into classical spacetime, like a ball rolling gently down a hill without a sharp cliff at the top. These models also change how we understand nothing. In classical terms, the singularity was a point of infinite something, infinite temperature, density, pressure, but in quantum genesis models, the beginning might emerge from a state of minimal or zero classical properties, a pre-geometry where the known quantities of space and time have no meaning. The universe doesn't come from a bang so much as a transition from a timeless, non-classical realm into the unfolding arena we live in now. What's especially exciting is that some of these ideas may be testable. Though we can't directly observe what happened the physics of the early universe left imprints. For example, the patterns of polarization and temperature in the cosmic microwave background could contain primordial gravitational waves, echoes of quantum fluctuations stretched by inflation. These signals, if found, could help distinguish between inflationary models and tell us whether quantum gravity truly erased the singularity. More provocatively, some theorists suggest that our universe might carry scars or patterns, subtle asymmetries, anomalies in the CMB, or patterns in the distribution of galaxies, that hint at a pre-Big Bang era. If we can decode these cosmic fossils, we might reconstruct a picture not only of the early universe but of its birth from a quantum gravitational state. In any case, the trend is clear. The idea of a singularity is giving way to a deeper, more nuanced understanding. A universe born not in a breakdown of physics, but in the emergence of physics. Not from a forbidden point, but from a quantum domain where the rules themselves evolved. So the next time we ask, what happened at the beginning of everything? We must refine the question. It may not be about a time when things began, but about a process through which space, time, and the laws of nature came into being. A transition from potential to actual. A phase shift in reality itself. This isn't just a scientific pivot, it's a philosophical revolution. Because it suggests that the cosmos was not thrust into existence by a singular eruption, but that it arose from the strange, creative depths of quantum gravity. It emerged not from a tear in space, but from the tapestry of possibility. In the earliest moments after the Big Bang, a universe no larger than an atom, searingly hot and unimaginably dense, everything was in a state of near-perfect symmetry. All the fundamental forces of nature were unified. All particles were indistinguishable. Every direction in space was the same. The laws of physics had not yet diversified. There was a kind of beautiful, total uniformity. No distinct forces, no distinct particles, no preferences or patterns. It was a balanced, seamless sea of pure potential. But this balance did not last. As the universe expanded and cooled, it underwent a dramatic and fundamental shift. That original symmetry, elegant and absolute, shattered. And in that breaking of symmetry, the seeds of structure were sown. The universe began to differentiate, to favor certain arrangements over others, to form distinctions where none had existed before. This process is known as spontaneous symmetry breaking, and it was one of the most transformative events in cosmic history. From it came the fundamental forces, the building blocks of matter, and eventually everything from atoms to galaxies. To understand this, let's begin with the concept of symmetry in physics. In simple terms, a system is symmetric if you can make certain changes, like rotating it, flipping it, or shifting it in space, without changing its behavior or properties. In the early universe, this symmetry was more profound than anything we experience in the visible world. All the known forces, gravity, electromagnetism, and the strong and weak nuclear forces, were once unified in a single superforce. The particles we now know as electrons, quarks, photons, and others were also unified, indistinct from one another. But as the universe expanded and cooled, this delicate balance became unstable. It's similar to how cooling water can transition from a uniform liquid to a structured solid, a process in which molecules choose positions, crystal lattices emerge, and symmetry is broken. In the early universe, something analogous happened. The forces began to freeze out and distinguish themselves from the undivided whole. The mechanism behind this breaking lies in the behavior of fields, particularly scalar fields like the Higgs field, which we will discuss in the next segment in greater detail. But for now, consider this: fields in physics are like invisible landscapes stretching across space. A field's value can vary from point to point, and the particles we observe are often excitations or ripples within these fields. Imagine a ball perfectly balanced at the top of a symmetrical hill. From the perspective of the ball, every direction is the same. There's no preference. But if that ball is nudged, even by the tiniest quantum fluctuation, it begins to roll. As soon as it picks a direction and moves, the symmetry is broken. The system now has a preference. Something once balanced and uniform is now uneven and differentiated. This metaphor describes what happened in the early universe. As the cosmos cooled, certain fields that were once symmetric became unstable at the high-energy state and fell into a lower-energy configuration, a new ground state, in which symmetry was no longer preserved. This shift is called a phase transition, and it has a deep analogy in thermodynamics, like water freezing into ice. One of the most important outcomes of this symmetry breaking is that it created diversity in the types of particles and forces that exist. For instance, the electromagnetic and weak nuclear forces were once part of a unified electroweak force. After spontaneous symmetry breaking, they split, giving rise to the electromagnetic force, which governs electricity and magnetism, and the weak nuclear force, which governs radioactive decay. Particles that had previously been massless and indistinct began to take on unique identities and properties. Some gained mass, others remained massless. Some interacted strongly with certain fields, others did not. The quantum fields of the early universe crystallized into a dynamic framework, a symphony of broken symmetry, that gave rise to everything familiar. And this breaking was not random chaos. It followed strict rules defined by the underlying quantum field theories, like the Standard Model of particle physics. The symmetry groups involved mathematical structures that describe how fields transform, predicted the kinds of particles and interactions that would emerge. From a theoretical standpoint, it was a kind of cosmic origami, where folding the fabric of symmetry resulted in the rich tapestry of physics we observe today. One fascinating consequence of symmetry breaking is the possibility that the early universe may have contained topological defects, leftover imperfections from this phase transition. These might include cosmic strings, domain walls, or monopoles, exotic structures that formed when different regions of space chose different configurations as the symmetry broke. While none of these have been definitively observed, some theories suggest they could still exist, hidden in the vast cosmic landscape. There's also a profound link between symmetry breaking and initial conditions. Before the breaking, the universe had no direction, no hierarchy, no structure. After the breaking, it had all of these. That's why symmetry breaking is sometimes called the moment creation began in earnest. It was the pivot from undifferentiated potential to specific, tangible existence. In this sense, spontaneous symmetry breaking was not just a physical event, it was the beginning of order, of variety, of individuality. It was the moment when particles could be born, when forces could act, when structure could form. It was when the formless took form. The great unbroken silence of the early universe gave way to a symphony of interaction, differentiation, and complexity. Without this broken symmetry, there would be no atoms, no molecules, no stars, no galaxies, no life. The same laws that seemed to break the unity of the early universe were, paradoxically, what made it possible for anything to exist at all. They turned potential into pattern, nothing into something, stillness into motion, and blankness into creation. In the aftermath of spontaneous symmetry breaking, the universe was filled with emerging forces and forming particles. But something critical was still missing: mass. While energy and motion had begun to take shape, most particles were still racing through the expanding cosmos at the speed of light, entirely massless. There was no way yet to slow them down, to give them the substance and inertia needed to become atoms, elements, planets, or living beings. What changed all that, what made matter matter, was the awakening of an invisible field, omnipresent and gentle, yet unimaginably influential, the Higgs field. To truly understand the significance of the Higgs field, we need to grasp a peculiar truth about fundamental particles. In their most pristine, symmetrical form, before symmetry breaking, many of them have no intrinsic mass. They're simply ripples in their respective fields, capable of existing, interacting, and moving, but with no weight to their existence. In this early universe, everything moved as if gliding across a frictionless floor. But as the universe cooled and symmetry broke, a hidden field turned on, pervading every inch of space. This field did not emerge in a dramatic burst. It was always there, sleeping in the fabric of the cosmos, waiting for the right conditions to awaken. The Higgs field is unlike other fields. It's a scalar field, meaning it doesn't have a direction in space like a vector field, e.g., the electric or magnetic fields. Instead, it has a constant value, a kind of ambient presence that exists everywhere. What makes it special is that, unlike the photon, which governs electromagnetism and remains massless, many fundamental particles gain mass only by interacting with the Higgs field. So how does this interaction work? Imagine a field that fills all of space, like an invisible ocean that particles must swim through. Some particles, like photons, move effortlessly. They don't feel the field at all. But others, like W and Z bosons, which mediate the weak nuclear force, and fermions like electrons and quarks, interact with the Higgs field in varying degrees. The more strongly a particle interacts with this field, the more it resists changes in motion, and this resistance manifests as mass. It's not the Higgs particle itself that gives mass, rather, it's the field. The Higgs boson, discovered at CERN in 2012, is simply the quantum excitation, the ripple, of that field. The true importance lies in the field's constant background value, known as its vacuum expectation value. This value breaks the electroweak symmetry and creates a new kind of landscape where particles gain identity, including mass. This is fundamentally different from how we usually think about mass. In Newtonian physics, mass is just an inherent property, like color or temperature. But quantum field theory teaches us that mass can be acquired. It's not something that particles are born with, but something they earn through their relationship with the Higgs field. This interaction is described mathematically through what's called a Yukawa coupling, which quantifies how strongly each particle couples to the Higgs field. This coupling is not universal. Some particles couple more, some less. That's why particles have different masses. The electron, for example, has a relatively small Yukawa coupling, so it interacts weakly with the Higgs field and thus has a small mass. The top quark, on the other hand, couples very strongly and is therefore very massive. And the photon, as mentioned, does not interact at all, which is why it remains massless and always travels at light speed. But why is mass important? Without mass, particles cannot clump together under gravity. They cannot form atoms, molecules, or anything complex. The early universe would have remained a smooth, uniform radiation soup, expanding endlessly but never forming stars, planets, or people. Mass gives particles inertia, the ability to resist acceleration, which allows for the stabilization of orbits, the creation of atoms, and the very architecture of the universe. Without the Higgs field, reality as we know it simply wouldn't exist. Moreover, the Higgs mechanism didn't just affect fermions like electrons and quarks. It also played a crucial role in shaping the weak nuclear force. Before the symmetry breaking, the electromagnetic and weak forces were unified in the electroweak force. But the Higgs field distinguished them by interacting differently with the carriers of these forces. The W and Z bosons, which mediate weak interactions, gain mass through the Higgs mechanism, while the photon remain massless. This is why the weak force is short-range, and the electromagnetic force is long-range. The mathematics of this transition is part of the Standard Model of particle physics, one of the most successful theories in all of science. It predicts how particles behave, how they interact with forces, and how mass emerges. Yet despite its power, the Standard Model has limits. It doesn't explain why the Higgs field has the value it does, or why the particle masses are what they are. It gives us how, but not always why. Still, the discovery of the Higgs boson was a monumental confirmation that we're on the right path, that this invisible field is real, and that the universe truly works in this subtle, astonishing way. There is also something eerie about the Higgs field's constancy. It's not enough that it exists, it must exist with a very particular value. If the Higgs vacuum expectation value were even slightly different, the masses of fundamental particles would change, the stability of atoms would collapse, and chemistry as we know it would be impossible. This delicate balance has puzzled physicists for decades and remains one of the central mysteries of modern science. Why does the Higgs field have this value? Why is the universe so finely tuned for life? Some have suggested that this is just a coincidence. Others propose deeper theories, like supersymmetry or the multiverse, to explain the apparent fine-tuning. But whatever the ultimate reason, the fact remains, the Higgs field, by turning on and permeating space, changed the universe from a ghostly dance of massless particles into a rich, solid, and structured world. It's easy to take mass for granted, to think of it as something basic and obvious. But in truth, mass is a mystery that took decades to solve. And the answer lies not in the particles themselves, but in their relationship with an omnipresent quantum field that fills the void with silent purpose. The Higgs field doesn't shout or sparkle. It doesn't push or pull. It simply is, and in being, it gives everything else the chance to be, too. With mass now embedded into particles through the quiet yet transformative awakening of the Higgs field, the universe was no longer just a soup of energy. It was a field of substance. Quarks and leptons, protons and electrons, began to form from the cooling primordial plasma. But there was something else, something fundamentally strange, that emerged with them. For every particle of matter, there appeared a corresponding twin, antimatter. This symmetry is one of the most elegant predictions in all of physics. According to the known laws of quantum field theory, every particle, whether it's an electron, quark, or neutrino, has a mirror opposite, called an antiparticle. These antiparticles are not imaginary, they are very real. They possess the same mass as their counterparts but have opposite charges. The antiparticle of the electron, for example, is the positron, identical in every way except that it carries a positive charge instead of a negative one. For protons, there are antiprotons. For neutrinos, there are antineutrinos. The laws of physics, especially the mathematics behind them, seem to require this kind of balance. In fact, when energy converts into matter, such as in high-energy collisions, it always creates a particle and an antiparticle together. This symmetry is so deep that it's encoded in the very fabric of the equations governing the early universe. And so, in those fiery first seconds after the Big Bang, as the energy of the cosmos condensed into mass, the creation of matter should have been perfectly mirrored by the creation of antimatter. For every billion quarks, a billion antiquarks. For every electron, a positron. The early universe should have been a pristine ballet of matter and antimatter partners spinning into existence in perfect harmony. But here's the enigma. When matter and antimatter meet, they annihilate. They vanish in a burst of energy, leaving behind nothing but light. This is not hypothetical, it's been demonstrated countless times in particle physics experiments. So if the early universe created equal parts of matter and antimatter, they should have destroyed one another completely. The universe, in theory, should be dark and empty, a sea of photons, but no stars, no galaxies, no atoms, and certainly no people. And yet here we are. We live in a universe overwhelmingly made of matter. All the stars, planets, and dust, all the elements forged in stellar cores, all of it is made of matter. We do not find equal amounts of antimatter drifting through the cosmos. In fact, we find almost none. When we search deep into space with gamma-ray detectors, we do not see the characteristic flashes that would come from regular matter and antimatter colliding. There are no antimatter galaxies. No anti-stars. No anti-planets. Somehow, matter won, and antimatter all but vanished. This discrepancy, the fact that the universe is dominated by matter despite theoretical predictions of perfect symmetry, is one of the greatest unsolved mysteries in modern physics. It's not just a scientific puzzle, it's a question about why anything exists at all. Why was there a tiny surplus of matter left over after all the mutual annihilations? Current estimates suggest that for every billion pairs of matter and antimatter particles that annihilated, just one extra matter particle remained. And it is from this tiny surplus, this fragile imbalance, that the entire material universe was built. That 1 in a billion anomaly is responsible for everything you've ever seen, touched, or known. But how did this imbalance arise? Physicists call this phenomenon baryon asymmetry, and it's the focus of intense theoretical and experimental research. There are several proposed mechanisms to explain it, theories that fall under the umbrella of baryogenesis. But before diving into those, we must first appreciate how remarkable this imbalance is. The laws of physics, as we understand them, are generally symmetric. They do not favor matter over antimatter. In fact, in most reactions, replacing a particle with its antiparticle and flipping charges and directions, an operation called CPT symmetry, produces a physically valid scenario. The laws still hold. Yet, somewhere in the early universe, something broke this symmetry ever so slightly, just enough to tilt the cosmic scale in favor of matter. The question is, what mechanism did it? What broke the perfect mirror? This is where we encounter the boundaries of known physics. The Standard Model does allow for a small violation of matter-antimatter symmetry, a phenomenon known as CP violation, which we'll explore in the next segment, but the amount of violation it predicts is far too tiny to account for the enormous dominance of matter we see today. So researchers believe there must be physics beyond the Standard Model at work here, undiscovered particles, new interactions, or previously unknown phases of the early universe that could explain this cosmic preference. Various hypotheses have been proposed. Some involve heavy, unstable particles that decayed asymmetrically into matter and antimatter. Others involve high-energy processes during cosmic inflation or during electroweak symmetry breaking that favored matter. Some even propose interactions involving neutrinos, those ghostly, nearly massless particles that barely interact with anything, as possible drivers of the imbalance through a mechanism called leptogenesis. Experimentalists are on the hunt. Facilities like CERN, Fermilab, and others are probing deeper into the matter-antimatter mystery, searching for tiny differences in behavior between particles and antiparticles. The hope is that by identifying new forms of asymmetry, we might inch closer to understanding why we exist at all. In the grand narrative of creation, this moment, this tipping of the scales toward matter, is perhaps the most delicate and consequential. A single extra quark in a billion. A solitary surplus particle in a universe of balance. And yet, from that sliver of asymmetry, a rich and complex cosmos emerged. It's humbling to consider how close we came to never existing. Had the universe been just a little more symmetric, we would not be here to ask the question. There would be no stars, no earth, no eyes to gaze up at the night sky and wonder how it all began. Instead, annihilation would have reigned. A cold, dark, perfect symmetry, lifeless and eternal. But that's not the universe we live in. Our universe is imperfect, and gloriously so. It is the asymmetry that gives us structure, story, and existence. The tiniest tilt in the early balance determined the fate of everything that followed. If the Big Bang produced equal amounts of matter and antimatter, and they annihilate when they meet, then why is there anything left? This isn't just a philosophical riddle, it's a physical paradox. According to our best understanding, there should have been nothing but light. But the fact that we're here means something tipped the balance. That tiny 1 in a billion excess of matter that survived wasn't a fluke, it was driven by a mechanism. That mechanism, as far as we know, is something called baryogenesis, the set of processes that may have created a surplus of baryons, the category of particles that includes protons and neutrons, over antibaryons in the early universe. Genesis implies a beginning. Baryo refers to baryons. So baryogenesis is literally the origin of matter. It's the hypothetical series of events that explains how and why matter gained the upper hand over antimatter in those first microseconds of cosmic time. Though we don't yet have a complete and confirmed theory of baryogenesis, we have several compelling ideas, each hinting at realms of physics beyond the standard model. Let's begin with the guiding principles. In the 1960s, Russian physicist Andrei Sakharov proposed 3 necessary conditions that any theory of baryogenesis must satisfy. These are known as the Sakharov conditions, and they remain the foundation for all modern theories that attempt to explain the matter-antimatter imbalance. First, baryon number violation. In our current universe, baryon number appears to be conserved, that is, the total number of baryons, like protons and neutrons, minus antibaryons stays constant in most observed processes. But if you want to go from a symmetric universe with equal amounts of matter and antimatter to one with just matter, you need interactions that violate this conservation. Otherwise, you could never end up with more matter than antimatter. So, the laws of physics in the early universe must have allowed for processes that could create more baryons than antibaryons. Second, C and CP violation. This refers to 2 kinds of symmetry. The C stands for charge conjugation, which flips a particle into its antiparticle. The P stands for parity, which flips spatial orientation, like a mirror image. CP symmetry means that the laws of physics should behave identically if you replace particles with their antiparticles and look in a mirror. If the universe treated matter and antimatter exactly the same, no imbalance could have formed. Therefore, for matter to dominate, these symmetries must be broken, and the early universe must have favored one over the other. We know CP violation exists. It's been observed in the decay of certain mesons, such as kaons and B mesons. But the amount of CP violation observed in the standard model of particle physics is far too small to explain the vast matter dominance we see. This means that there must be undiscovered sources of CP violation, and uncovering them is one of the great goals of modern particle physics. Third, departure from thermal equilibrium. In a perfectly balanced thermal equilibrium, like a pot of boiling water kept at a constant temperature, creation and annihilation processes happen at equal rates. You can't get a net change unless something disturbs that equilibrium. In the early universe, as it rapidly expanded and cooled, it underwent phase transitions, like a liquid freezing into a solid. These were the moments when the cosmic conditions were out of balance, and it's precisely in these chaotic, transitional times that baryogenesis could have occurred. Non-equilibrium conditions allow small asymmetries to freeze in and persist as the universe cools. With these three Sakharov conditions in mind, baryon number violation, CP violation, and departure from thermal equilibrium, let's explore the leading theoretical ideas for how baryogenesis might have played out. One major class of theories involves something called GET baryogenesis, based on grand unified theories. These are speculative models that propose that at very high energies, much higher than we can currently test, the electromagnetic, weak, and strong nuclear forces were all unified into a single superforce. In this framework, heavy particles called X bosons or Y bosons could decay in ways that violate baryon number and CP symmetry. As these massive particles decayed during the universe's earliest instance, they could have preferentially produced more matter than antimatter. Unfortunately, these theories predict phenomena, like proton decay, that have not yet been observed, but the mathematical beauty of unification keeps this possibility alive in theoretical circles. Another idea is electroweak baryogenesis, which ties the asymmetry to the electroweak phase transition, the moment when the unified electroweak force split into the electromagnetic and weak nuclear forces. If this transition were a first-order phase transition, like water boiling into steam with bubbles and violent dynamics, it could have created expanding bubbles of the new phase throughout the universe. Within the walls of these bubbles, out-of-equilibrium conditions would have allowed for CP-violating processes to take place, resulting in a net baryon number. The Standard Model almost allows for this, but the phase transition it predicts is too smooth and gradual, not violent enough to do the job. However, in extensions of the Standard Model, such as supersymmetry, this phase transition could be stronger and more abrupt, reviving this mechanism as a viable path to baryogenesis. There's also the intriguing theory of leptogenesis. This idea shifts the focus from baryons to leptons, particularly the neutrinos. Neutrinos are incredibly light and barely interact with normal matter, yet they are abundant and carry potential clues to the origin of matter itself. Some theories propose that in the early universe, heavy right-handed neutrinos, which do not exist in the Standard Model but are predicted in many extensions, decayed in a CP-violating way to produce more leptons than antileptons. Then, through processes involving sphalerons, topological solutions in electroweak theory, this lepton asymmetry could be converted into a baryon asymmetry. This idea is especially compelling because it connects the matter-antimatter imbalance with the mystery of neutrino masses, suggesting that both could be explained by the same physics. All of these mechanisms are compelling, but none have yet been proven. They remain mathematical frameworks, theoretical scaffolds for what might have happened in those first fleeting seconds. Experimental physics is still working to catch up. Powerful accelerators like the Large Hadron Collider and dedicated experiments on CP violation in B factories are helping to test some of these ideas. Neutrino experiments like DUNE and Hypercameo-Candy are poised to look for the signs of leptogenesis by studying the behavior of neutrinos and antineutrinos with unprecedented precision. But even if we do find the missing piece, that elusive interaction or particle that explains why matter came to dominate, it will likely point to something bigger. Something beyond what we now know. Baryogenesis, then, is not just a key to understanding matter, it's a doorway to new physics, to the parts of the universe that still hide behind the veil of the unknown. The irony is that the tiniest imbalance, just one extra particle in a billion, may hold the deepest secrets of creation. That fragile asymmetry was enough to prevent a cosmic void and instead give rise to everything: galaxies, stars, oceans, and minds capable of asking why. The story of baryogenesis is the story of how the universe became biased towards something rather than nothing. And in that preference, encoded in the laws of physics and frozen into the fabric of space-time, lies the reason we are here. To truly understand how the universe ended up with more matter than antimatter, we have to take a closer look at a phenomenon so subtle, so delicate, that it barely shows itself, yet its consequences may be the reason we exist. This phenomenon is called CP violation, and though it might sound like an obscure bit of particle physics jargon, it sits at the heart of one of the greatest cosmic mysteries. Why does anything exist at all? Let's start with the basics. In physics, C stands for charge conjugation, the idea that the laws of nature should behave the same if every particle is replaced by its antiparticle, its mirror opposite in terms of electric charge. So, a negatively charged electron would become a positively charged positron. P, or parity, means flipping the spatial coordinates, as if you're looking in a mirror. Combine them, and you get CP symmetry, which assumes that the universe should look and behave the same even if you swapped matter for antimatter and viewed everything in reverse. In an ideal, perfectly symmetric universe, the rules governing the behavior of particles would be identical to those for antiparticles, just mirrored. That means if you start with a perfectly balanced mix of matter and antimatter, and they evolve under CP symmetric rules, they should annihilate one another in equal measure, leaving behind nothing but radiation. That would be the end of the story. No stars, no planets, no you. But that's not the universe we live in. Something small, tipped the balance ever so slightly. Something violated CP symmetry. It didn't treat particles and antiparticles exactly the same. And that tiny deviation, though barely detectable, was just enough to allow a sliver of matter to survive the great annihilation. This is the role of CP violation, a subtle asymmetry in the laws of physics that causes matter and antimatter to behave just a little differently. The first hints of CP violation were discovered in the 1960s. In an experiment at Brookhaven National Laboratory, physicists observed that neutral kaons, subatomic particles made of a quark and an antiquark, sometimes decayed in a way that violated the expected symmetry between matter and antimatter. This was shocking. Until then, it was assumed that CP symmetry was absolute. But here was experimental proof that the universe played favorites, not in a dramatic way, but in a barely noticeable, fractional deviation from balance. Further studies confirmed this strange behavior. The standard model of particle physics was revised to include CP violation, particularly through something called the CKM matrix, which describes how quarks can change flavors during weak nuclear interactions. Within this matrix, there's a complex phase, a source of asymmetry, that allows for CP violation in decays of certain mesons. But here's the catch. While this built-in CP violation exists, and is experimentally verified, it's far too weak to explain the matter-antimatter imbalance we observe in the universe. The standard model's CP violation contributes, but it's like using a teacup to fill an ocean. We need something more. That realization has led physicists to search for new sources of CP violation, ones that might lie beyond the standard model. For example, there may be CP-violating processes in the behavior of neutrinos, or in interactions involving as yet undiscovered particles. These additional asymmetries could have been active in the high-energy conditions of the early universe, long before the forces of nature cooled and settled into the forms we observe today. Why is CP violation so crucial in the early universe? Because it's not enough just to have a process that creates matter and antimatter. If that process treats both sides equally, they'll always annihilate in equal amounts. But if there's a slight preference for matter, a tiny nudge in the equations, then over time, that preference gets locked in. During the rapid cooling and phase transitions after the Big Bang, CP-violating interactions could have caused particles to be created more often than antiparticles. These particles, having just a bit more presence, would ultimately become the universe's building blocks. The rest, the antimatter, would meet its fate in a firestorm of mutual annihilation. Experiments today are continuing the search for new kinds of CP violation. Physicists are studying B mesons and D mesons, looking for unexpected behavior and how they decay. The LHCb experiment at CERN is one of the world's most advanced tools for this purpose, and it has already found small discrepancies that point to deeper complexities in the rules that govern matter. Still, none of this has yet explained the magnitude of the cosmic imbalance. Some researchers are also investigating CP violation in the lepton sector, specifically involving neutrinos. If neutrinos and antineutrinos behave differently when they oscillate, changing from one flavor to another, it could be a critical clue. This is where experiments like DUNE, the Deep Underground Neutrino Experiment, come into play. By sending beams of neutrinos across vast distances and observing how they change, scientists hope to measure CP violation in the lepton sector and determine whether this asymmetry could help account for the dominance of matter. Another compelling possibility lies in the idea of heavy right-handed neutrinos, hypothetical particles that don't interact with the weak nuclear force and would have been produced in abundance during the early universe. If these particles decayed in a CP-violating way, favoring leptons over antileptons, then, through the magic of Sphaleron processes, this lepton imbalance could be converted into a baryon imbalance. This is the heart of leptogenesis, which ties CP violation directly to the birth of matter through neutrino physics. What's fascinating is that these tiny asymmetries, almost imperceptible in modern experiments, might have had colossal consequences in the high-energy furnace of the early cosmos. The early universe was a realm where quantum fields surged, decayed, collided, and crystallized into new forms. In that environment, even the slightest preference for matter could amplify over time. CP violation, barely visible in the echo of today's particles, might have echoed thunderously across those early moments, shaping everything that followed. And let's pause here to reflect on what that means. The laws of nature are not perfectly balanced. They are ever so slightly biased. Not in a way that breaks them, but in a way that gives them character, and gives us a universe. It's as if the universe leaned toward matter with a barely perceptible sigh, and that sigh echoed through every atom and star. That whisper of imbalance, that flaw in the mirror, is why you exist. To understand how the universe conjured solid, tangible matter from pure, intangible energy, we need to revisit one of the most iconic and profound equations ever devised, E equals mc squared. Though it looks simple, this elegant expression from Albert Einstein carries within it the secret blueprint for how the early cosmos transformed from a radiant sea of energy into the matter-filled universe we see today. It bridges the worlds of the invisible and the solid, the energetic and the inertial, and it explains how, in the earliest moments after the Big Bang, energy became matter. Let's unpack the equation. E stands for energy, m for mass, and c superscript 2 is the speed of light squared, an enormous number. This tells us that even a small amount of mass contains an extraordinary amount of energy. But the reverse is also true. If you have enough energy, under the right conditions, that energy can be converted into mass, into actual particles. This is exactly what happened in the early universe. During the first fractions of a second after the Big Bang, the universe was unimaginably hot and dense. The energy levels were so high that particles of matter and antimatter could spontaneously appear from the quantum fields, as long as they obeyed conservation laws. These weren't static particles drifting through space. They were constantly colliding, annihilating, and being reborn from the tremendous energy all around them. This moment was governed by thermodynamics, quantum mechanics, and general relativity all at once. The extreme temperatures, reaching up to Kelvin, created an environment where energy and mass were fluidly interchangeable. Just as water can evaporate into vapor or condense into liquid, so too could energy condense into particles. Particles emerge not by miracle but through statistical certainty. When enough energy is crammed into a small enough space, matter will emerge. At these early stages, matter and antimatter particles, like electrons and positrons, quarks and antiquarks, were being created and annihilated in constant equilibrium. Every time two photons, particles of light, collided with enough combined energy, they could produce a pair of particles, a particle and its antiparticle. This is known as pair production, and it's been observed in laboratory experiments as well. When high-energy gamma rays interact near an atomic nucleus, they can turn into an electron-positron pair. But in the early universe, these interactions were happening everywhere, all the time, and at an unfathomable scale. Photons, the most energetic entities in the young cosmos, were constantly crashing into each other, turning into pairs of matter and antimatter. Then those pairs would annihilate back into photons, keeping the system in dynamic equilibrium. So the key takeaway is this: matter came from energy, and Einstein's equation was the rulebook for how this transformation unfolded. This raises an interesting philosophical point too, that matter is not fundamental in the way we often imagine. Matter is, in some sense, frozen energy. It's a condensed, structured form of something far more abstract and versatile. That chair, that planet, that person, all are ultimately forms of energy, locked into mass by the early alchemy of the cosmos. This realization also highlights how finely tuned those first few moments were. The energy density of the early universe had to be just right. If it were too low, there wouldn't have been enough raw material, not enough energy to make matter. If it were too high for too long, the universe might have collapsed back in on itself, or re-expanded too quickly for matter to form stable structures. But as it turns out, the energy level, expansion rate, and cooling curve followed just the right path to allow energy to birth matter, and for matter to survive. As the universe expanded, it cooled. Once it dropped below a certain energy threshold, pair production could no longer occur efficiently. The photon collisions no longer had enough punch to create particle-antiparticle pairs. That process ceased, and the only matter left was what had not annihilated, that tiny surplus we discussed earlier, left behind by CP violation and preserved by baryogenesis. That tiny residue became everything: stars, galaxies, oceans, consciousness. In a way, we owe our existence to the cooling of the universe, a gradual loss of energy intensity that forced the universe to crystallize into something more permanent. Energy gave way to matter, just as steam condenses into droplets. The heat of existence gave way to form. There's also something deeply poetic in knowing that matter is not some eternal, immovable object, it is energy wearing structure. Everything we see, touch, and are was once pure light and heat. We are, quite literally, cooled down energy stabilized into atoms, molecules, and eventually cells and thoughts. Moreover, E=mc² doesn't just explain how the universe began. It governs every nuclear reaction in the stars. When the sun shines, it is converting mass into energy, the reverse of what happened at the dawn of time. Through nuclear fusion, hydrogen nuclei merge to form helium, and the small difference in mass is emitted as energy, the light and warmth that bathes our world. In stars, mass becomes energy. In the Big Bang, energy became mass. This duality is one of the most profound truths of nature, that mass and energy are two sides of the same cosmic coin. Einstein's insight opened the door to understanding not just nuclear reactions, but the very birth of matter itself. And when we speak of the early universe, cooling down, enough for matter to form, we're really talking about energy folding itself into more stable, massive forms. So, when the universe was young, hot, and dense, it created matter not by magic but by following this deeply rooted equivalence. The energy of the Big Bang wasn't just explosive chaos. It was potential, waiting to coalesce into the building blocks of everything. It's a reminder that the structure of the cosmos is not random. It follows rules, elegant, mathematical rules that link the invisible to the visible. When we look at the universe today, we don't just see matter, we see fossilized energy, arranged by time, shaped by space, and governed by Einstein's equation. Everything began as raw energy, transformed into the tapestry of galaxies and consciousness through the mechanics of E=mc². From that single insight comes a sweeping narrative, that light can become stone, that fire can become flesh, and that from energy alone, the universe found a way to become real. As the universe expanded and cooled, the chaos of its fiery birth slowly gave way to structure. The dance of particles and antiparticles dwindled, leaving behind a delicate excess of matter. Energy transformed into mass. Subatomic particles combined to form protons and neutrons, which later fused into light elements like hydrogen and helium. But during those first few 100,000 years, the universe was still a seething fog, dense, hot, and utterly opaque. Photons, the particles of light, couldn't travel freely because they constantly scattered off charged particles like electrons and protons. The cosmos was like a glowing fog of plasma, impenetrable to the light that filled it. Then something extraordinary happened. Roughly 380,000 years after the Big Bang, the universe had cooled to about 3,000 Kelvin, a temperature cool enough for electrons and protons to combine into neutral hydrogen atoms. This moment is called recombination, and it was a turning point in cosmic history. With the formation of neutral atoms, free electrons all but disappeared, and photons were no longer constantly bouncing off charged particles. Instead, they were free to move, to stream across the universe without being scattered. That flood of newly liberated photons was the first light of the universe, not in the metaphorical sense, but quite literally the first light able to travel freely through space. This moment marks the transition from an opaque universe to a transparent one. It's the last scattering surface, the point beyond which we can no longer see, because earlier light was endlessly bounced around. And though that light has been traveling ever since, it has changed in a remarkable way. As the universe expanded, space itself stretched, and with it, the wavelengths of those photons stretched too. What began as a blindingly hot flash of light in the visible spectrum has, over billions of years, cooled and redshifted into the microwave part of the electromagnetic spectrum. This ancient glow, this afterglow of creation, is what we now call the cosmic microwave background, or CMB. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson while they were experimenting with a microwave antenna, the CMB was the final, undeniable evidence that the universe had a hot, dense origin, what we now call the Big Bang. At first, the discovery was puzzling. They were trying to calibrate their equipment, and couldn't get rid of a strange, persistent noise. No matter where they pointed the antenna, they picked up a faint background signal, one that seemed to come from all directions equally. What they had found was the echo of the Big Bang. The CMB is cosmic fossil light, a snapshot of the universe when it was just 380,000 years old. It's not just background static, it's a map of the early cosmos, frozen in time. With satellites like COBE, WMAP, and Planck, scientists have measured the CMB with exquisite precision, revealing a smooth, nearly uniform glow with tiny variations in temperature, just a few parts in 100,000. These slight differences are crucial. They are the seeds of all future structure. Those temperature fluctuations are the imprints of quantum fluctuations that were stretched during inflation, tiny variations in density that eventually grew into galaxies, clusters, and voids. They are the fingerprints of the earliest processes, echoing the story of how matter began to organize itself into the complex what we see today. When we look at the CMB, we are quite literally looking back in time. Not metaphorically, literally. The light reaching us today has been traveling through space for 13.8 billion years. It began its journey when the universe was a mere infant, and it has not interacted with matter since. It's like a photograph taken of the universe's baby picture, preserved and stretched over the entire sky. But what does the CMB tell us about matter and its creation? First, it confirms that the universe had a thermal beginning, a hot, dense phase from which matter emerged. Second, it shows that the early universe was incredibly uniform, but not perfectly so. The tiny deviations in temperature and density tell us that quantum fluctuations, likely amplified by inflation, laid the groundwork for the cosmic structures we see today. And perhaps most importantly, the CMB tells us about the composition of the universe at that early stage. By analyzing the detailed spectrum of the CMB, the specific intensity of different microwave frequencies, scientists can determine the relative abundance of ordinary matter, and dark energy. And the results are astounding. Ordinary matter, the kind we're made of, makes up only about 5% of the total energy content of the universe. The rest? Roughly 27% is dark matter, and about 68% is dark energy. So the CMB doesn't just show us where matter came from, it also tells us how rare it is. That delicate, 1 in a billion surplus of matter over antimatter was enough to seed everything we know. The galaxies, the stars, the atoms in your body, all of them owe their existence to the tiny imbalances frozen into the CMB. It's a cosmic message written in microwave radiation, telling the story of how a universe once filled with pure energy became a universe filled with matter and structure. And this message surrounds us, constantly. The CMB is present everywhere in the sky. If your television ever displayed static on an old antenna signal, a small percentage of that noise, around 1%, was the CMB. The rest was local noise, but that tiny fraction was literal evidence of the universe's origin, reaching into your living room from the edge of time. As technology has advanced, our ability to map the CMB has become more refined. The Planck satellite, for example, provided the most detailed map ever created, allowing scientists to calculate the universe's age, geometry, and composition with astonishing precision. Through the CMB, we've confirmed that the universe is 13.8 billion years old, flat on large scales, and expanding at an accelerating rate. And yet, for all its data and precision, the CMB remains something deeply poetic. It is the light from when the universe took its first breath, finally free to expand and cool into the stars and galaxies that would one day give rise to eyes capable of seeing it. The cosmic microwave background is the glowing testament that energy cooled into matter, and that matter cooled into atoms, and those atoms into the building blocks of all we see. It is the ultimate relic of matter's birth, a whisper from the earliest epoch, still echoing through the vast halls of space-time. The story of matter's formation is like the unfolding of a cosmic symphony, from the briefest of quantum fluctuations to the grand structures of galaxies and clusters. Each phase followed a precise order, a cascade of events that turned raw energy into stable matter, and stable matter into the vast, luminous tapestry we call the universe. The timeline of this transformation stretches across epochs, each governed by its own physics, thresholds, and pivotal transitions. Understanding this journey not only gives us insight into the nature of matter, but also reveals just how incredibly fine-tuned and orchestrated the cosmos truly is. We begin at time zero, the Big Bang itself, a moment when the universe was unimaginably hot and dense, with all forces unified and no matter as we know it. Just fractions of a second in, the universe entered the Planck epoch, lasting from time zero to seconds. During this period, gravity was still unified with the other fundamental forces, and the energy scales were so extreme that we currently lack a working theory. We need quantum gravity to describe what happened here, and that remains one of the greatest unsolved problems in physics. Next comes the grand unification epoch, lasting until about seconds. During this time, the strong nuclear force split off from the electroweak force, marking the first symmetry breaking of the fundamental interactions. The universe was still a seething foam of pure energy, no matter yet, just an intensely hot soup of fluctuating quantum fields. Then came a pivotal moment, cosmic inflation. Somewhere around 2 seconds, the universe underwent a brief but violent exponential expansion, increasing its size by a factor of at least in a blink of time. Quantum fluctuations that were subatomic in scale were stretched to cosmic proportions. This event smoothed out the geometry of the universe, flattened space-time, and seeded the density variations that would later grow into galaxies. When inflation ended, it dumped a tremendous amount of energy into the universe, a process known as reheating, and that's when the production of particles truly began. What followed was the quark epoch, lasting from about seconds to seconds. During this time, the universe had cooled just enough for energy to condense into elementary particles, quarks and gluons. But the temperatures were still too high for these particles to combine into anything stable. Instead, the universe was a quark-gluon plasma, a chaotic mix of these fundamental building blocks, constantly interacting and exchanging energy. As the universe cooled further, it entered the hadron epoch, beginning around seconds. At this point, quarks began to bind together via the strong nuclear force to form hadrons, particles like protons and neutrons. Gluons, the carriers of the strong force, stitched quarks together in triplets, forming the first stable composite particles of matter. But with the formation of hadrons also came the inevitable clash with their antimatter counterparts. Protons and antiprotons, neutrons and antineutrons, all of them were produced in pairs, and they annihilated each other in fiery flashes of gamma rays. However, due to the slight asymmetry in the early universe, a tiny excess of matter over antimatter, some protons and neutrons survived. This surplus, a relic of baryogenesis, became the seed of all matter we observe today. A few seconds after the Big Bang, the universe entered the lepton epoch, dominated by lightweight particles like electrons, positrons, and neutrinos. These leptons interacted with the photon field, keeping the universe opaque and thermally dynamic. Annihilation continued between electrons and positrons, again leaving a small excess of electrons, enough to eventually balance the positive charge of protons and form neutral atoms later on. By about 1 second after the Big Bang, neutrinos decoupled from matter and began to free stream through space. These neutrinos are still out there today, forming a cosmic neutrino background, a barely detectable bath of ghostly particles from the earliest moments of creation. Then came the nucleosynthesis epoch, also known as Big Bang nucleosynthesis, which occurred between about 3 minutes and 20 minutes after the Big Bang. During this brief window, the universe had cooled to a temperature around Kelvin, and conditions were just right for nuclear fusion. Protons and neutrons combined to form the first light nuclei, primarily helium-4, along with trace amounts of deuterium, helium-3, and lithium-7. This set the elemental composition of the universe for the next 100 million years. However, the universe was still too hot for electrons to bind with nuclei. For the next 380,000 years, it remained a hot plasma, a fog of nuclei, electrons, and photons. But eventually, the temperature dropped below 3000 Kelvin. That's when we reached the recombination epoch, when electrons could finally combine with nuclei to form neutral atoms. Photons, no longer constantly scattering off free electrons, were freed, and this gave us the cosmic microwave background, the afterglow of this grand transition. With the universe now transparent, the Dark Ages began, an era with no stars, no galaxies, just cold hydrogen and helium atoms drifting through expanding space. Gravity, however, was working silently. Over millions of years, the slightly denser regions of matter, seeded by inflationary fluctuations, began to collapse under their own gravity. This gave rise to the cosmic dawn, around 100 million years after the Big Bang. The first stars, known as population 3 stars, ignited. These stars were massive, short-lived, and composed almost entirely of hydrogen and helium. They burned hot, exploded as supernovae, and seeded the surrounding space with heavier elements, carbon, oxygen, iron, the building blocks of future generations of stars, planets, and life. The intense ultraviolet radiation from these early stars also began to reionize the neutral hydrogen gas, marking the beginning of the epoch of reionization. Over the next several 100 million years, galaxies and quasars contributed to this ionizing light, gradually restoring the ionized state of the universe. By about 1 billion years after the Big Bang, the first galaxies began to form. Stars gathered into gravitationally bound structures, spinning into spirals or merging into ellipticals. The large-scale structure of the cosmos emerged, a web of filaments and clusters stretching across hundreds of millions of light-years. From then on, the process of cosmic evolution became one of structure and complexity. Galaxies collided, merged, and evolved. Stars were born, aged, and died. The heavier elements created in supernovae enriched the interstellar medium, allowing for rocky planets, complex chemistry, and eventually, life. And all of it, every atom in your body, every star in the sky, every distant galaxy, began as a quantum ripple in an ocean of pure energy. That ripple became a fluctuation, the fluctuation became a particle, the particle became a proton, and the proton became part of a star. From seconds to 13.8 billion years, the universe's timeline of matter formation is not just a sequence of physical transitions. It's the unfolding of potential into form, of energy into structure, of emptiness into awareness. Could the universe have created itself? At first glance, the idea seems paradoxical. How can something exist before it exists? And how can a cosmos burst into being without anything to cause it? But modern physics has dared to ask this question not just philosophically, but mathematically and scientifically. As strange as it may seem, there are serious, well-considered theories suggesting that the universe didn't need a cause in the traditional sense, that it could have spontaneously emerged from the fabric of quantum reality itself. To begin with, we have to set aside our intuitive notions of time, cause and effect, and even existence. In everyday experience, everything that begins has a cause. A tree grows from a seed. A person is born from parents. A fire starts from a spark. But when we talk about the origin of the universe, we're dealing with an event that includes the beginning of space and time themselves. There was no before, in the usual sense. Time itself was created in that moment, so causality, as we understand it, may not apply at all. This leads us into the domain of quantum cosmology, where the rules of quantum mechanics are applied not to particles, but to the entire universe. Here, one of the boldest proposals comes from theoretical physicists like Stephen Hawking and James Hartle, who introduced the idea that the universe might not require a beginning in the conventional sense. In their no-boundary proposal, the universe has no edge, no starting point in time as we imagine it. Rather, time behaves like a spatial dimension in the earliest moments, smoothly rounding off without a singular beginning. In this framework, the universe could emerge from a quantum fluctuation, much like virtual particles flicker into and out of existence in the quantum vacuum. The vacuum, despite its name, is not empty. It seethes with potential, governed by uncertain energies and virtual events. If this can happen at the level of subatomic particles, could it happen on a cosmic scale? That's exactly what some theories suggest, that the universe tunneled into existence from a quantum state of nothing. This is not nothing, as in emptiness or blankness, but a state with no classical space or time, governed instead by the probability waves of quantum physics. According to quantum tunneling, particles can appear on the other side of an energy barrier even if they seemingly don't have enough energy to get there. It's a statistical event, not a deterministic one. In a similar way, the universe itself could be a quantum tunneling event, transitioning from a pre-existence of timeless probability into the reality we now inhabit. This idea was advanced by physicist Alexander Vilenkin, who proposed a model in which the universe came from nothing, as a quantum tunneling event, not from an existing space, but from a truly non-spatial, non-temporal state. In Vilenkin's words, "The universe is the ultimate free lunch." From this perspective, the laws of quantum mechanics and gravity might allow space and time to blossom from a state of no space and no time, with the whole universe popping into existence with a tiny, finite volume, and then undergoing inflation to grow into the cosmos we see today. This spontaneous emergence doesn't violate any known physical laws, because physical laws themselves aren't material things that need a pre-existing universe to exist in. They're more like mathematical truths, timeless relationships that may exist independently of time itself. The laws don't act, they permit. And if they permit the spontaneous birth of universes, then our existence is simply a realization of that permission. But this leads to a deeper question. Why do these laws exist in the first place? If the universe could create itself from quantum rules, then we must ask, where did the rules come from? Are they eternal? Are they necessary? Or did they arise along with the universe itself? Some physicists argue that the laws of physics are self-contained, that they don't require an external lawgiver or metaphysical framework. In this view, the mathematical structure of reality is simply the way things are, and if such a structure makes a universe inevitable, then that universe will, eventually, pop into existence. Just like numbers exist without needing someone to invent them, the potential for a universe may exist in a similar abstract way, waiting to realize itself. Others go further, proposing that universes are constantly appearing in a vast multiverse, born from the quantum vacuum in an infinite cycle of spontaneous births. In such a multiverse, our universe would be just one of countless bubbles emerging from an eternal, chaotic quantum sea. Each bubble might have different physical constants, different dimensional structures, or even different laws altogether. This leads to the anthropic principle, the idea that we observe this universe with these particular laws because these are the conditions under which life, observers, and questions can exist. But not all scientists are comfortable with these ideas. Critics argue that appealing to spontaneous creation might explain how, but it still doesn't explain why. Why does the quantum vacuum exist at all? Why are there laws governing it? Why is there something rather than nothing? These are questions that may lie beyond the reach of physics. Science can tell us what's possible within a given framework of laws and models, but it struggles to account for the framework itself. If the universe created itself from quantum laws, that answers part of the puzzle. But whether those laws are fundamental or emergent remains an open mystery. Nevertheless, the idea that the universe created itself, or at least emerged without an external cause, is a compelling one. It reframes existence not as a miracle imposed from without, but as a natural, if deeply mysterious, phenomenon arising from the deepest structures of reality. It means the universe may not be the result of something else, but rather the unfolding of a possibility that was always there. And when we look out into the night sky, at galaxies drifting through the void, at stars burning for billions of years, at the light from 13 billion years ago still washing over us, we're not just seeing the aftermath of a creation. We may be seeing a universe that is its own explanation, a cosmos that emerged not from nothing, but from the strange, rich, restless fabric of quantum reality itself. What if everything we see, every galaxy, star, planet, atom, even your own body, added up to nothing? It might sound absurd, but this is precisely what the zero-energy universe hypothesis proposes. It's one of the most elegant, mind-bending, and counterintuitive ideas in cosmology, that the total net energy of the universe is exactly zero. To understand how this can be possible, we need to explore two key types of energy that are fundamental to the cosmos: positive energy, which is stored in matter and radiation, and negative energy, which exists in the form of gravity. Let's begin with the obvious. Matter contains energy, lots of it. Thanks to Einstein's famous equation, we know that mass is equivalent to energy. Every atom in your body, every star lighting up the sky, every black hole lurking in the darkness, all of it holds enormous amounts of positive energy. This also includes all forms of radiation, like light and heat, and even the kinetic energy of objects in motion. But what often goes unnoticed is that gravity has negative energy. This isn't just a poetic metaphor, it's a rigorously supported concept in physics. Gravitational potential energy is negative because it takes energy to separate massive objects. Imagine trying to pull the Earth and the Moon apart. You'd have to do work, to exert effort, and that means adding energy into the system. The further apart the objects, the more positive energy you've added, so conversely, the closer they are, the more negative gravitational energy the system has. Gravity acts like a cosmic debt ledger, balancing out the energetic assets of matter and motion with a matching liability. So here's where the idea becomes truly profound. If you add up all the positive energy from mass, radiation, and motion, and then subtract the negative energy from gravitational interactions, the sum might be exactly zero. This is not just speculation. Some of the most well-respected physicists, including Stephen Hawking, Alan Guth, and Lawrence Krauss, have entertained this possibility as a serious explanation for how the universe could spontaneously arise from nothing, because, in energy terms, nothing had to be invested. You could think of it like this: the universe is a kind of perfect financial transaction, positive energy borrowed from one account, exactly cancelled by negative energy from another. No net cost. A cosmic free lunch. In inflationary cosmology, this idea plays a central role. When inflation occurred, the brief, explosive expansion of space-time just after the Big Bang, it required energy to fuel it. But where did that energy come from? The zero-energy universe hypothesis suggests that the positive energy of inflation was balanced by the negative energy of the gravitational field being created simultaneously. As the universe expanded, space itself was created, and with it, gravity. This expanding space carried negative energy, precisely offsetting the inflationary energy that drove expansion. In this way, the entire universe could have emerged from a quantum fluctuation, as we discussed previously, without violating the conservation of energy. Because there was nothing to begin with, and the final tally still adds up to nothing, the creation of the universe could be a net zero event, not in carbon emissions, but in total energy. It's worth noting that this idea only works if gravity truly has negative energy, and that's something supported not just by theoretical physics, but also by observations of gravitational systems. The behavior of galaxies, black holes, and even the curvature of spacetime in general relativity reinforces this interpretation. In fact, it's precisely because gravity is attractive that it has negative potential energy. The closer things are pulled together, the more deeply in debt the system becomes. Now let's explore the implications. If the total energy of the universe is zero, then in some deep sense, the universe doesn't need a cause in the traditional sense. It didn't require an external energy input. The universe could exist because it is energetically neutral, like a vacuum fluctuation that never needed to be paid for. It's not just that the universe came from nothing, it's that it still is nothing, just arranged in a more interesting way. Think of a hill and a valley. If you pile up dirt to make a hill and dig a hole to make a valley, you've rearranged the earth, but you haven't added or removed any net soil. The hill is positive height, the valley is negative. Together they cancel. In the same way, positive matter energy and negative gravitational energy can be viewed as a topological rearrangement of nothingness into somethingness, but without altering the total sum. Some critics of the hypothesis argue that defining total energy in general relativity is not always straightforward. Energy conservation is clean and simple in Newtonian physics and special relativity, but general relativity, which deals with curved spacetime, introduces complications. There's no single, globally conserved energy in the same way. However, in the context of an expanding, homogeneous, and isotropic universe, as modeled by inflationary cosmology, the zero-energy assumption appears to be valid and consistent. And what about the vacuum energy, or dark energy, that's accelerating the universe's expansion? This too might be part of the equation, perhaps a reservoir of potential energy stored in space itself, balancing gravitational energy even now. In this view, the universe continues to evolve as a zero-energy system, playing out its destiny without ever tipping the energetic scale in any direction. So when we ask, how could the universe come from nothing? The zero-energy hypothesis gives a surprisingly satisfying answer: it didn't cost anything. The universe is like a cosmic check that wrote itself, a perfect balance of opposites, where existence and non-existence are two sides of the same energetic equation. This doesn't explain why the laws of physics are arranged in such a way that this is possible, but it shows that within the rules of modern physics, a universe from nothing isn't just plausible, it may be inevitable. And when we look out at the stars, we're not just seeing matter and energy, we're seeing the beautiful balance of forces and fields that still adds up to the most profound number in the cosmos: 0. Even now, billions of years after the birth of the cosmos, the universe continues to surprise us. It's no longer expanding at a constant rate. In fact, it's not just expanding, it's accelerating. Galaxies are racing away from each other faster and faster, driven by something invisible, untouchable, and still deeply mysterious. This phenomenon, dark energy, is not only reshaping our cosmic future, but also reinforcing an astonishing truth: even the vast, empty vacuum of space is not truly empty. It's filled with energy. And this energy might be the very thing propelling the universe apart. To appreciate the magnitude of this idea, let's rewind for a moment. 4 decades after the Big Bang theory gained widespread acceptance, scientists believed that the expansion of the universe would eventually slow down. After all, gravity pulls things together. As matter spread out from the explosion-like beginning of time, its own gravity was expected to act as a cosmic brake, tugging galaxies back and potentially even leading to a future contraction, the so-called Big Crunch. That was the prevailing view. But everything changed in the late 1990s, when 2 independent teams of astronomers, the Supernova Cosmology Project and the Higgs Supernova Search Team, studied the light from Type I supernovae, which serve as cosmic mile markers. By measuring their brightness and redshift, scientists could determine how fast the universe was expanding in the past. What they found was shocking. The distant supernovae appeared dimmer than expected, suggesting they were farther away than they should be. This meant the expansion of the universe hadn't been slowing down, it had been speeding up. This discovery led to the revival of a term first introduced, and then discarded, by Albert Einstein: the cosmological constant. When Einstein formulated general relativity, he initially included a constant term to keep the universe static. But once Hubble discovered cosmic expansion, Einstein abandoned the idea, calling it his greatest blunder. Yet here it was again, back with a vengeance, not as a mistake, but as a possible feature of space itself. What we now call dark energy could very well be this cosmological constant, an intrinsic property of space that exerts a repulsive force, counteracting gravity on cosmic scales. Unlike matter or radiation, which dilute as the universe expands, the energy associated with space itself doesn't thin out. As more space is created through expansion, more dark energy appears, keeping its density roughly constant, and causing the expansion rate to accelerate. So where does this dark energy come from? One of the leading candidates is vacuum energy, the energy that remains when all particles, forces, and radiation are stripped away from a region of space. This concept comes straight from quantum field theory, where every point in space is governed by fields that cannot be completely nullified. Even when a field is in its lowest possible energy state, its vacuum state, it still fluctuates. These fluctuations are not imaginary, they are real and measurable, as evidenced by phenomena like the Casimir effect, in which two uncharged metal plates placed very close together in a vacuum attract each other due to shifts in vacuum energy between them. In other words, nothing is still something. It seethes with energy, particles popping in and out of existence, virtual fields oscillating in the background, and complex interactions taking place even in regions devoid of any traditional matter. If vacuum energy is indeed responsible for dark energy, then the universe is being driven apart by the energy of emptiness. But there's a problem. When physicists attempt to calculate the vacuum energy predicted by quantum field theory, the numbers they get are absurd, off by a factor of 10 superscript 1 superscript 2. That's a 1 followed by 120 zeros, the largest known discrepancy between theory and observation in all of science. It's called the cosmological constant problem, and it's a towering unsolved mystery. Why is the vacuum energy so much smaller than what theory predicts? Why is it not zero? And why does it seem to have just the right value to begin accelerating the universe precisely when galaxies and stars have had time to form, but not earlier? These are open questions, ones that hint at deeper physics we don't yet understand. Some scientists propose that dark energy may not be constant, but instead evolves with time, a dynamic form of energy called quintessence. Unlike the fixed energy density of a cosmological constant, quintessence would change as the universe evolves, perhaps waxing or waning in influence. However, current observations still favor a constant, unchanging dark energy, though new data from telescopes like the James Webb Space Telescope and future missions like Euclid and Nancy Grace Roman may provide deeper insights. But whatever form it takes, dark energy dominates the universe today. It makes up about 68% of the total energy content of the cosmos. That means the overwhelming majority of the universe is composed of something we can't see, can't touch, and barely understand, a silent, pervasive force embedded in the very geometry of space-time. It's worth emphasizing again, this energy isn't stored in particles, or fields that occupy space, it is a property of space itself. The more space there is, the more dark energy there is. And as the universe expands, space creates more of itself, making the effect self-sustaining and increasingly dominant over time. Eventually, dark energy will determine the fate of the cosmos. If it continues as a cosmological constant, galaxies beyond our local group will drift away faster and faster, eventually disappearing from view entirely. Stars will burn out, new ones will stop forming, and the universe will grow cold, dark, and empty, a lonely, silent expanse ruled by the energy of nothingness. In a strange way, this suggests that the universe may end not with a bang, but with a fade, driven by the same vacuum energy that may have given it birth in the first place. From quantum fluctuations in the early vacuum, to dark energy pulling galaxies apart, nothingness has always played a central role in everything. It's not merely the absence of matter or energy, it's an active player in the story of the cosmos. The empty void is alive with possibility, power, and mystery. It created us, and one day, it may erase all signs that we ever existed. To probe deeper into how the universe might have arisen from nothing, we have to enter the strange and beautiful world of quantum cosmology, the application of quantum mechanics to the universe as a whole. Here, the question isn't just how particles behave within the universe, but how the universe itself, as a quantum object, could come into existence. This is not just a matter of extrapolating physics backward in time, It's about fundamentally reimagining what it means for the universe to begin. One of the most revolutionary and philosophically profound proposals in this realm is the Hartle-Hawking no-boundary proposal, developed in the 1980s by physicist James Hartle and the legendary Stephen Hawking. This idea radically redefines our understanding of the beginning of time, or rather, the lack of a beginning. In traditional cosmology, the universe starts with a singularity, a point of infinite density and temperature, where the known laws of physics break down. It's a mathematical abstraction, not a physical object we can observe or touch. While this singularity marks the limit of our knowledge, it poses a deep problem. If time begins there, what existed before? What conditions caused it? The Hartle-Hawking model aims to solve this by removing the singularity entirely. Their proposal suggests that, in the earliest stages of the universe, in the tiny fractions of a second before the Big Bang, time itself behaved like a spatial dimension. In other words, there was no distinct point at which time began, in the classical sense. Instead of a hard edge or boundary where the universe suddenly springs into existence, time smoothly curves and transitions, much like the surface of a sphere has no edge, no sharp corners, and no boundary. It just is. Imagine standing at the South Pole. Every direction you walk is north, but there's no southernmost point beyond which you can't go, because you're already at it. The no-boundary proposal views the beginning of the universe in a similar way. The Big Bang is not a singularity with a sharp beginning, but more like the rounded cap of a higher dimensional surface. There's no before, not because it's hidden, but because it doesn't exist in any meaningful physical sense. Time itself, as we experience it, is an emergent property of this quantum geometry. This approach uses a mathematical technique called Wick rotation, which essentially transforms time from a real to an imaginary number, in a complex number sense, during calculations. When time is treated as imaginary in the earliest moments, the geometry of the universe becomes smooth and Euclidean, like a sphere. Then, as the universe expands and cools, time transitions from imaginary to real, and our familiar experience of linear, ticking time emerges. The Hartle-Hawking wave function, a central result of their theory, gives the probability amplitude for different possible universes. In this framework, universes with certain properties are more likely to tunnel into existence than others. The most probable universes are those that are smooth, small, finite, and without boundaries, just like our own early universe appears to be. The wave function doesn't tell us which universe will happen. Quantum theory doesn't deal in certainties, but it offers a distribution of likely cosmic histories. This has staggering implications. It means the universe didn't need a cause in the traditional sense because its existence is a quantum event, much like how radioactive atoms decay without a trigger. There's no need for a prior moment, no edge where creation must be invoked. The universe simply is a quantum fluctuation of geometry, a bubble in the space-time foam. And Hartle and Hawking weren't alone in their efforts. Other models in quantum cosmology have attempted to tackle the origin problem in different ways. One example is Vilenkin's tunneling proposal, which we discussed earlier, where the universe tunnels from nothing, a state with no space, time, or energy, into existence via quantum effects. This model emphasizes the probabilistic, non-deterministic nature of the universe's birth, much like a particle quantum tunnels through a barrier. Then there's the loop quantum cosmology approach, which arises from loop quantum gravity, an attempt to quantize spacetime itself. In this framework, space is made of discrete loops of quantum geometry, and time may not be continuous. According to some versions of this theory, the universe didn't begin at a singularity, but bounced, collapsing from a previous contracting phase and rebounding into expansion. This big bounce model avoids the singularity problem and replaces it with a cyclical cosmic history. Other speculative models include the ekpyrotic universe, derived from string theory, where our universe results from a collision of higher dimensional branes in a multiverse landscape. Still others propose eternal inflation, where inflation never ends globally, but continues spawning new bubble universes, like ours, each one a separate pocket in a much larger, ever-growing quantum foam. What ties all these models together is the idea that quantum rules govern not only particles and forces, but the very structure and existence of space and time themselves. In quantum cosmology, the birth of the universe is not seen as an event caused by something external, but rather as a spontaneous emergence from a timeless, law-governed quantum substrate. It's important to recognize that these models are not without controversy. We can't yet test them directly, and they often deal with realms of energy, geometry, and dimensionality that lie far beyond current experimental reach. But they are built on the best mathematical and physical principles we have, combining general relativity's smooth geometry with quantum mechanics' probabilistic nature, in a courageous attempt to answer the oldest question of all: why is there something rather than nothing? And perhaps the answer is stranger and more beautiful than we ever imagined, that our entire universe is the outcome of a quantum possibility, one that required no boundary, no trigger, and no cause, just the profound and eternal capacity of nature to become. If one universe can spontaneously arise from a quantum vacuum, then what's to stop more from forming? Could our cosmos be just one of an uncountable number, a single bubble floating in an endless sea of universes? This is the heart of the multiverse possibility. The idea that reality may be far larger, stranger, and more complex than our observable universe suggests. It's not science fiction. It's a serious, if speculative, consequence of some of the most successful theories in modern physics. To begin unpacking this, let's return to the theory of cosmic inflation, the brief, exponential expansion of space in the first tiny fractions of a second after the Big Bang. This theory was originally proposed to explain several perplexing features of our universe, such as why it appears so flat, homogeneous, and isotropic on large scales. But once inflation theory was developed, physicists realized something remarkable. Inflation doesn't have to end everywhere at once. In fact, it probably doesn't. This leads to the concept of eternal inflation. In this scenario, while inflation may have ended in our region of space, giving rise to the hot Big Bang and the observable universe, it continues elsewhere, indefinitely. Space keeps inflating in a chaotic, fractal-like way, and within this inflating backdrop, pockets of space can stop inflating, forming bubble universes. Each bubble is a separate universe, potentially with its own laws of physics, constants, particles, and dimensions. Ours is just one bubble in this ever-expanding froth, a vast multiverse. And what causes these bubbles to form? The very same quantum fluctuations we've been discussing. In the quantum foam that fills the inflating space, fluctuations can push different regions over the threshold where inflation ends locally. As each bubble nucleates, it stops inflating, begins cooling, and develops its own unique history, like the birth of our own universe. But the inflating space outside the bubble never stops. It just keeps going, spawning more and more bubbles, eternally. The implications of this are staggering. First, if the multiverse is real, then our universe is not the universe, but just one of many. Our laws of physics, such as the speed of light or the strength of gravity, might be just local features, not fundamental truths of reality, but environmental variables, different in other universes. Just as Earth has just the right conditions for life to arise, our universe might have the right physical parameters to allow atoms, stars, chemistry, and observers, while others don't. This leads naturally to the anthropic principle, a controversial but philosophically potent idea. It states that we observe the universe to be the way it is because we exist in it. In a multiverse with countless possibilities, most universes might be lifeless, chaotic, or short-lived. But we, conscious beings capable of asking questions, could only exist in a universe that permits complexity and stability. In that light, our universe doesn't need a special explanation for its apparent fine-tuning. It's not that the universe was made for us, it's that we exist in the only kind of universe that would allow us to. Some physicists resist this reasoning, arguing that it's untestable or unfalsifiable. If other universes are causally disconnected from ours, separated by inflating space we can never reach, then how could we ever observe them? Are we invoking an idea that's metaphysical rather than scientific? Yet despite this, hints of the multiverse may be visible in our own cosmic backyard. Some researchers have speculated that collisions between bubble universes might leave imprints in the cosmic microwave background, subtle, circular scars or temperature anomalies. So far, no convincing evidence of such collisions has been found, but the search continues. And beyond observational signs, the multiverse is deeply woven into the mathematics of quantum field theory, string theory, and inflationary cosmology. So deeply, in fact, that it might be harder to avoid the multiverse than to accept it. In string theory, for instance, the landscape of possible universes is vast, perhaps on the order of 10 or more, each with its own way of curling up extra dimensions, choosing vacuum states, and determining physical constants. This string landscape suggests a natural multiverse, where different patches of the cosmos settle into different configurations of the fundamental fields. Our universe would be just one such patch, and the reason it supports life is because the majority don't. There's also the many worlds interpretation of quantum mechanics, which posits that every time a quantum event occurs with multiple possible outcomes, the universe splits, and all outcomes happen in parallel. If this is true, then an unfathomable number of universes are constantly branching off from every decision, every random event, every quantum fluctuation, including ones where you chose a different career, or where dinosaurs never went extinct, or where the laws of physics diverged ever so slightly. While these ideas may seem extreme, it's important to note, the multiverse isn't a hypothesis born from wild speculation. It's an emergent feature of multiple lines of respected, rigorous theoretical work. Inflation leads naturally to eternal inflation. Quantum mechanics leads naturally to many worlds. String theory leads naturally to a vast landscape of possible universes. These are not disconnected ideas. They're converging signals pointing toward the same breathtaking possibility. We are part of a much larger, perhaps infinite, cosmic reality. Of course, this doesn't come without deep philosophical consequences. If there are infinite universes, does that mean every possibility is real somewhere? Are there exact copies of you in other universes, making different choices? Does free will still make sense in such a context? What does it mean to be unique in an infinite multiverse? And what does it say about our universe, the one we can see and measure? Perhaps it means that our universe is not special in any cosmic sense, but it is special to us. It is the stage on which all of human history, thought, and wonder has unfolded. It is the one universe where you are you. And maybe, just maybe, that's enough. The multiverse doesn't diminish our existence, it magnifies it, by showing how precious and improbable this particular version of the cosmos truly is. At the heart of our journey lies one of the most haunting, ancient, and unanswerable questions ever conceived by the human mind: can something come from truly nothing? This question echoes across both scientific inquiry and philosophical contemplation, and in many ways, it defines the boundary between what we understand about the universe and what still lies beyond the grasp of reason, observation, and logic. To even ask if something can come from nothing, we must first wrestle with the slippery nature of the word nothing. It's a word that seems simple, a lack of anything, but the moment we examine it closely it dissolves into paradox. In philosophy, nothing refers to absolute non-existence. No matter, no space, no time, no energy, no laws, no possibility. Not an empty room, not a vacuum, not even empty space, but the complete absence of being. And yet this is not the same nothing that science refers to when it speaks of quantum fields or vacuum fluctuations. In physics, nothing is much more nuanced and far less empty. When scientists talk about the vacuum, they refer to quantum nothing, which is actually a seething, active, frothing field of possibility. Even when all particles are removed, the vacuum of space remains full of quantum fields in their lowest energy states. These fields cannot be zeroed out entirely. Thanks to the Heisenberg uncertainty principle, fluctuations inevitably arise. Virtual particles appear and vanish, fields jitter and foam. This vacuum isn't lifeless, it's a stage of constant movement, where the fabric of reality itself never fully rests. From this scientific nothing, it's conceivable that the universe could have sprung. Quantum cosmology models, such as Vilenkin's tunneling proposal or the Hartle-Hawking no-boundary wave function, envision the universe not emerging from absolute non-existence, but from a pre-geometric quantum state. In this view, time and space were not present before the universe, because before has no meaning when time itself doesn't yet exist. The universe emerged from a timeless, law-governed mathematical structure, a kind of potentiality waiting to be realized. But can this really be called nothing? Critics, especially from philosophical traditions, argue that this quantum vacuum is not nothing at all. It has laws. It has structure. It has fields, energy, and mathematical descriptions. Even the very capacity for quantum fluctuation assumes a framework, rules of behavior that exist in some form. So if the universe arose from a quantum vacuum, it didn't arise from nothing, but from something deeply fundamental and profoundly mysterious. In other words, physics has pushed the line of creation back to a state of minimal structure, but not all the way to pure, metaphysical nothingness. This raises a profound philosophical tension. If science cannot speak of creation from absolute nothing, is there any way to even conceptualize such an event? Would it make any sense to say, nothing gave rise to something, if by nothing we mean truly no existence whatsoever? Is that even a coherent sentence? Can there be causality without time, or a transition from non-being to being without a framework to contain it? These questions reveal the limits of human reason and the tools of scientific language. Science is astonishingly powerful at modeling and predicting the behavior of things once they exist. But when confronted with the edge of existence itself, the transition from not being to being, science can only speak in models, probabilities, and hypotheses grounded in physical rules. When we ask why the laws themselves exist, or why anything exists rather than nothing, we drift into philosophical territory where the rules of mathematics may no longer suffice. Some philosophers have suggested that nothingness may be unstable in a similar way to how symmetry is unstable, that existence might be more likely than non-existence simply because being is more flexible than non-being. In this view, nothing is not a default, but a state that cannot hold, a kind of false vacuum that decays into reality. But this presupposes the rules by which that instability operates, again raising the question, where do those rules come from? Others argue from the principle of plenitude, the idea that all possible realities must exist, including ones that spontaneously come into being from nothing. Some cosmologists even suggest that the laws of physics themselves are emergent, not eternal, but forming in the same instant as the universe itself. This would mean that not just space and time, but the entire rulebook of the cosmos, sprang into being simultaneously, without cause, without precedent, and without a prior canvas. In this picture, nothing is not a passive void, but an active condition pregnant with potential, not unlike how a blank canvas holds the capacity for infinite paintings. The question becomes not why something came from nothing, but how nothing managed to give rise to such a precise, structured, and knowable something. Still, the idea of true nothingness remains one of the most vexing conceptual voids we can attempt to peer into. It may be that the human mind, evolved to navigate the material world, is not well equipped to fathom the absence of all things, not just objects, but the context in which objects can exist. We may never be able to fully articulate what nothing means, because all language, thought, and logic presuppose something to talk about. And yet, this mystery continues to captivate thinkers across disciplines. The question of why there is something rather than nothing has been called the ultimate question of existence, and it remains open, raw, and thrillingly unresolved. Whether the answer lies in future theories of quantum gravity, deeper mathematical insights, or entirely new frameworks of thought, one thing remains clear: from the edge of nothingness, a universe emerged, stars ignited, atoms formed, consciousness arose, and we now gaze back toward that edge, still seeking answers. If the universe is governed by laws, patterns so stable, so mathematically elegant, that they can be written down in symbols and tested with stunning precision, then the natural question is, where did these laws come from? Are they eternal, pre-existing truths woven into the abstract fabric of reality? Or did they emerge along with the universe itself, born from the very same spark that ignited space and time? To imagine that the laws of physics are eternal is to suggest that they exist independently of the physical universe, that they are timeless mathematical structures or logical necessities. In this view, even if there were no matter, no space, no time, the laws themselves would still exist, in some abstract, perhaps Platonic sense. They are not material objects, but relations, ratios, equations, like 2 plus 2 is equal to 4, which is true whether or not anyone is there to count. This is a compelling idea, especially to mathematical Platonists, who argue that mathematical truths are discovered, not invented. The same might apply to the laws of physics. They are out there, waiting to be found, universal and eternal. But this raises a dilemma. If the laws predate the universe, where are they located? In what medium do they exist? If there is no time, no space, no matter, no mind, how can these laws be anything at all? Are they just logical possibilities that happen to get realized when a universe begins? On the other hand, the alternative view, that the laws are self-originating, suggests they did not exist before the universe, but arose with it. Just as space, time, and matter began with the Big Bang, so too did the rules that govern them. This would mean that the laws of nature are not absolute, but contingent. They are a product of our universe's birth conditions, not prerequisites to it. In this sense, the laws are more like outcomes, byproducts of the initial state of the cosmos, crystallizing as the universe cooled and expanded. If this is true, then the laws could have been different. And indeed, many physicists believe they could be. In string theory, for example, the laws of physics depend on how extra dimensions are curled up. Different configurations lead to different particles, constants, and interactions. This gives rise to the so-called landscape of possible universes, each with its own laws, where ours is just one of many. That would mean the laws of physics aren't universal at all, just local settings, like a cosmic dial turned to the life possible position. And yet, even in this landscape model, we face another layer of mystery. What governs the landscape itself? What framework allows different laws to arise? Are there meta-laws that dictate how physical laws can vary? These questions push against the limits of what current science can test or verify. But they also remind us of something deeper, that our universe, with its elegant laws and intelligible structure, may not be the only way that reality can be. Whether its laws are written in the stars from eternity or scribbled in the first sparks of creation, their very existence remains one of the most breathtaking and humbling facts of all. Time, so familiar, so constant, ticking forward without pause, yet so elusive when we try to define it. We measure our lives by it, track the motions of planets with it, and run our experiments by its flow. But when we ask whether time existed before the universe, we're forced to rethink everything we think we know. The classical view, rooted in Newtonian physics, treated time as an absolute backdrop, a ticking cosmic clock that runs uniformly for all events, regardless of location or motion. In this view, it makes sense to ask, what happened before the Big Bang? Because time is seen as something that exists independently of everything else, like a theater in which the cosmic drama unfolds. But modern physics, particularly Einstein's theory of general relativity, changed that picture dramatically. In Einstein's universe, time is not separate from space. It's woven into the fabric of space-time. Space and time form a single four-dimensional continuum, and that fabric can bend, stretch, twist, and even come to a halt under extreme conditions. This means time is not an independent stage, it is part of the set, shaped by the matter and energy within it. According to the standard Big Bang model, as we trace the universe backward, space contracts and density increases, and so does temperature and energy. At a certain point, about 13.8 billion years ago, the universe becomes so hot, dense, and curved that the equations of general relativity break down. This is the so-called singularity, where time, as we understand it, ceases to have meaning. In fact, many physicists believe that time itself began with the Big Bang. If time is a property of the universe, something that came into existence with the universe, then there was no before the Big Bang. Not because it's unknown, but because the concept of before requires time to exist in the first place. Asking what came before time is like asking what's north of the North Pole. It's a question that presupposes a direction where none exists. Yet, other models in cosmology offer alternative views. In quantum gravity models like loop quantum cosmology, the singularity is replaced with a bounce, a prior universe contracting and rebounding into our own. In that view, time may not have a beginning, but instead stretches infinitely in both directions. Likewise, string theory and eternal inflation suggest that our universe may be one of many, a bubble in a multiverse, with its own internal timeline. Time might exist differently, or not at all, in the regions outside our bubble. Then there's the no-boundary proposal from Hartle and Hawking, which redefines the origin entirely. Time, in the earliest moments, behaved like a spatial dimension. The Big Bang wasn't a singular explosion in time but a smooth, rounded origin with no sharp edge, and no before. Time, as we know it, emerged from this state, unfurling from a timeless condition into the familiar forward-flowing arrow we experience. So, did time exist before the universe? It depends entirely on how we define time and universe. If time is a relational property, born from motion and change, then it's meaningless without a universe to host it. But if time is more fundamental, a kind of raw potentiality for sequence and transformation, perhaps it existed in a hidden form, waiting to be revealed. Whatever the truth, our understanding of time is still evolving. And as we chase the origins of matter, energy, space, and structure, we're beginning to realize that time may be the greatest mystery of all, not just a backdrop to creation, but one of the most profound consequences of it. After exploring the birth of time, the emergence of laws, and the origin of matter itself, a sobering and necessary question remains: can we ever truly know the origin of everything? Is the mystery of creation something science can ultimately solve, or will it forever lie beyond the horizon of what is knowable? At its core, science is a method, a tool for building models of the universe based on evidence, experiment, and mathematical consistency. It thrives in environments where hypotheses can be tested and predictions confirmed. When applied to the vast cosmic history of the universe, this method has proven astonishingly powerful. From the structure of atoms to the behavior of galaxies, we've built a stunningly accurate narrative of how things unfolded from the first fraction of a second to now. We've mapped the cosmic microwave background, measured the expansion rate of the universe, simulated the formation of stars and galaxies, and even recreated conditions of the early universe and particle accelerators. We've shown how the laws of physics can, in theory, explain the emergence of complexity from simplicity, and perhaps even something from quantum nothing. But when it comes to the true origin, the very first cause, the source from which the laws, time, and space itself may have emerged, we find ourselves at the edge of science's current power. This is partly because the earliest moments of the universe involve energies and conditions that go beyond anything we can currently replicate or observe. To understand the first trillionth of a second, we would need a complete quantum theory of gravity, a framework that combines the probabilistic world of quantum mechanics with the curved spacetime of general relativity. Despite brilliant efforts from theories like string theory and loop quantum gravity, we have no final theory yet. And until we do, the birth of the universe remains, at least partially, hidden. There are also epistemological limits, boundaries to what we can know, even in principle. If something existed, before time, or outside our universe, and it has no causal contact with us, then we may never have access to any data about it. It would be like trying to reconstruct a novel from a single word, an impossible task, not because the novel didn't exist, but because too much of it lies beyond our reach. This doesn't mean we stop asking. On the contrary, it is in the asking that progress is made. The limits of knowledge are not fixed. They expand with every new theory, every new observation, every new insight into how nature works. At one point in history, people thought we'd never know what stars were made of. Later, they thought atoms were indivisible, or that nothing could escape a black hole. Each unbreakable limit was eventually broken by deeper understanding and better tools. Today, we are closer than ever to answering questions that, for most of human history, were reserved for myth and philosophy. We have models that describe the evolution of the universe with extraordinary precision. We have quantum theories that show how particles can arise spontaneously. We have the beginnings of a unifying theory that could explain both gravity and quantum mechanics. But we must also be humble. Some aspects of reality may be fundamentally unknowable, not because of a failure in science, but because of the structure of reality itself. Quantum mechanics, for example, teaches us that uncertainty is built into the universe. In some cases, questions may not have well-defined answers. And perhaps the origin of everything, the moment where nothing became something, is one of those questions. Still, the pursuit itself is a triumph. It shows that the human mind, emerging from matter, shaped by evolution, grounded in experience, can reach outward to the very edge of reality and ask why. Whether we ever arrive at the final answer or not, the journey changes us. It expands our sense of wonder, deepens our humility, and connects us to the vast story of existence in a way that transcends mere facts. Maybe one day we'll know. Maybe we'll discover a theory so elegant, so complete, that it explains not only how the universe began, but why it had to begin that way. Or maybe the answer is beyond science, and the most honest response we can give is all. If the universe truly came from nothing, no time, no space, no particles, no cause, then everything we are, everything we see, and everything we ever will be is the result of a spontaneous and law-bound unfolding of a void. This idea is as staggering as it is humbling. It shifts the weight of our very existence from something grounded and solid to something delicate, contingent, and infinitely strange. What does it mean to live in such a universe? It means, first of all, that existence is not guaranteed. It's not necessary. It's not inevitable. If something can emerge from nothing, it also implies that nothing might just as easily have remained nothing. The fact that we exist at all, that atoms formed, that stars ignited, that life evolved, that consciousness arose, is not some obvious outcome. It's a cosmic surprise. And yet here we are. This understanding changes our relationship with reality. It reframes existence not as a given, but as a precious and improbable state. It brings a kind of reverence, not for a creator necessarily, but for the astonishing fact of being. A universe from nothing doesn't diminish the miracle of life. In fact, it may magnify it. Because when you start with absolutely nothing, even the simplest particle becomes a kind of miracle. Living in such a universe also means living without a built-in purpose, at least not one that's externally imposed. If the cosmos is the product of random fluctuations, symmetry breakings, and emergent laws, then it didn't come into being for us. We are not the center of the story. We are a recent addition to a narrative billions of years in the making. And yet our consciousness allows us to reflect on that narrative, to study it, question it, and even reshape it. That, too, is remarkable. It also raises existential questions. If everything came from nothing, then so did meaning, at least at the beginning. Meaning didn't arrive prepackaged with the universe. It emerged over time, just as matter did, just as structure and life and awareness did. Meaning, in this sense, is not handed to us, it's created by us. In a universe that came from nothing, meaning is not found. It's built. This realization can be terrifying. But it can also be liberating. It means we are not bound by some cosmic script. We write our own stories. We create value, purpose, and significance, not in spite of a meaningless beginning, but because of it. Our very freedom to shape meaning is a direct consequence of the openness, the raw potential, that came from nothingness. Moreover, understanding that the universe may have no ultimate reason for existing doesn't rob it of beauty. On the contrary, it highlights the fragile wonder of everything around us. The patterns of snowflakes, the orbit of moons, the laughter of children, all of it, in a way, shouldn't exist at all. But it does. And that makes each moment, each breath, each thought, profoundly precious. It may also deepen our empathy. If everything came from nothing, and yet gave rise to us, beings capable of suffering, joy, love, and curiosity, then perhaps our most sacred duty is to cherish that experience, and to protect it. Not because the universe demands it, but because we have the capacity to choose it. Because we are the only beings we know of who can even ask what any of this means. To live in a universe that came from nothing is to live in a story that defies logic, expectation, and certainty. It's to walk the razor's edge between chaos and order, between insignificance and wonder. And while the origin of all things may remain elusive, hidden behind the veil of the quantum vacuum, or encoded in timeless mathematics, the implications for us are immediate. We are the product of a universe that had no reason to be, and yet it is. And so are we. From the deepest and most silent void, a place beyond space, before time, beneath even the barest whisper of substance, everything began. Not with a sound. Not with a spark. But with a trembling, invisible shift. A moment when not being was no longer still, and the universe became. There were no stars then. No galaxies. No atoms. Not even laws. Just the gentle birth of structure, unwinding from mystery. A bloom of space-time swelling outward, silent, immense, and impossibly young. From that first breath of expansion, the ingredients of reality were scattered like seeds. Quarks danced into existence. Photons filled the empty stretches. Time took its first step forward, and with it, everything we would ever know. And yet, if the models hold, if quantum fields and symmetry breakings and inflationary landscapes speak truth, then what we now call reality may have emerged not from something, but from nothing. Not nothing as in an empty space. Not a blank room, nor a dark abyss. But true nothing, the absence of space, the absence of time, the absence of form or substance or spark. And still, it came. The stars were born. Hydrogen lit the sky. Galaxies swirled in cosmic spirals, pulled by invisible forces, gathering light into the firmament. Planets spun into orbit. Oceans filled. Life bloomed. Eyes opened. Minds awakened. Thought emerged, thoughts that could reflect on stars, on atoms, on the mystery of their own beginning. We became not only a product of the cosmos, but its mirror. A way for the universe to observe itself, to wonder at its own existence. To ask why it is here at all, and to shudder in awe at the possibility that nothing, in all its silence, held more power than we ever imagined. Perhaps the most profound truth isn't that something came from nothing, but that from nothing came not only stars, but meaning, consciousness, wonder. And so, in a universe that may have no ultimate purpose, we make our own. We write our stories on a canvas of space and time, formed by laws we barely understand, emerging from an origin we may never fully grasp. And yet, the story is real. We are real. From nothing, everything. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.